Welcome back, everyone. Today we're diving deep into one of the strangest chapters in Earth's history, the Archean Eon, when our planet was an ocean world with rising continents, violent volcanoes, and a very different sky. If you enjoy this kind of long-form science journey, please remember to hit the like button, subscribe to the channel, and share this video with someone who loves geology and space. Your support really helps these projects keep going. Thank you so much for watching, and now let's step back billions of years and see what Earth was really like in its earliest oceans. The young sun shines on the inner solar system with a light that is weaker than in later ages, yet its activity remains intense. The Archean Earth moves along its orbit within this changing field of radiation and particles. The star emits strong ultraviolet light streams of charged particles and frequent flares. These outputs shape the space environment that surrounds the planet. The early solar wind, a steady flow of particles from the sun, is stronger than in later times and presses against the thin envelope of gas around the Earth. Between the sun and the planet stretches a space filled with dust, fragments of rock and ice remnants from planet formation. The inner system is less crowded than in the Hadean, but large asteroids and comets still cross the path of the Earth at long intervals. Each object carries a specific mix of minerals, metals, and volatile compounds that will take part in the planet's later history. From a distant view, the Archean Earth is a small, bright sphere with a developing atmosphere and a large satellite. The Moon orbits closer than it does in later times, so its apparent size in the sky of Earth is greater, and its gravity has a stronger effect on the planet. The pair moves together through space, locked in their mutual orbit around the Sun. Light from the star falls on the day side of the Earth, heating the surface and upper layers of the ocean, while the night side faces the dark of space and cools. High above the surface, the upper atmosphere interacts directly with the solar wind and high-energy radiation. Some particles and molecules are lost from the top of the atmosphere, but the overall mass of gas remains sufficient to blanket the surface and support liquid water. The balance between gained and lost material is controlled by the combined effects of impact's interior outgassing and escape to space. In the broader inner solar system, other rocky planets follow their own orbits, each with its particular combination of atmosphere and surface conditions. Mars, smaller and cooler, already shows signs of loss of internal heat and atmospheric thinning. Venus, similar in size to Earth, is likely moving toward a dense hot atmosphere with strong greenhouse conditions. Numerous small bodies inhabit the asteroid belt between Mars and Jupiter, and some of these will slowly change orbits under the influence of gravitational interactions. Comets, which are ice-rich bodies from more distant reservoirs, occasionally pass through the inner regions on elongated paths. When an asteroid or comet path crosses that of Earth, the chance of an impact arises. Over Archean time, the frequency of very large impacts is lower than during the late heavy bombardment, but sizable collisions still occur on timescales of many millions of years. Each impact adds material to the Earth and briefly disturbs its surface and atmosphere. Rocky projectiles deliver silicate minerals and metals that merge with existing crust or sink toward the interior. Ice-rich bodies contribute water and other volatile compounds, such as carbon dioxide and simple carbon-bearing molecules. When an impact occurs, kinetic energy converts into heat-melting rock at the site of collision, and sometimes causing localized vaporization of surface water and atmosphere. Ejecta, which are fragments of rock thrown into the air and space, can leave the planet or fall back as a layer of debris. In very large impacts, global effects are possible, including temporary heating of the atmosphere and surface, and episodes of intense rain as vaporized water condenses and returns to the ground and ocean. Over long spans of Archean time, however, these disturbances are episodic features within an overall trend toward a more stable surface and persistent oceans. The Sun's energy output is lower in total brightness than in later periods, a circumstance sometimes called the faint young sun. Yet the Earth does not freeze. The reason lies in the combined effects of greenhouse gases in the atmosphere, internal heat flow from the planet's interior, and the pattern of cloud formation. Volcanic outgassing and ongoing chemical reactions release gases such as carbon dioxide, water vapour, and likely methane into the air. These gases absorb outgoing infrared radiation from the surface and re-radiate it, helping to keep the lower atmosphere warm enough for liquid water. The balance between the weaker incoming solar radiation and stronger greenhouse trapping sets a range of surface temperatures that allow oceans to exist. From the vantage point of space, this balance appears as a steady emission of infrared radiation from the planet, matched on average to the incoming energy from the Sun. The magnetic field of the Earth also plays a role in shaping the space environment near the planet. A dynamo in the liquid outer core generates a global magnetic field that extends outward into space as a magnetosphere. This region deflects many of the charged particles from the solar wind, guiding them around the planet, rather than allowing them to strike the upper atmosphere directly. Some particles become trapped in belts or follow magnetic field lines toward the polar regions, where they deposit energy high above the surface. By reducing direct particle erosion of the atmosphere, the magnetosphere helps to retain gases that are important for climate and ocean stability. The shape and strength of this magnetic shield change over geological time as the core and mantle evolve, but during the Archean it already acts as an important modifier of the interaction between solar wind and atmosphere. In this setting, the flux of material and energy from space to Earth continues at a moderate pace. Small dust particles and micrometeoroids enter the atmosphere every day, burning up and adding trace elements to the upper layers of air and to the surface when they settle out. Occasional larger impacts produce craters on land and basins in the seafloor, though many of these later structures are erased or altered by tectonic and erosional processes. The overall result is a slow accumulation of extraterrestrial material that complements the internal building and reshaping of the planet. Over Archean time, the rate of incoming large bodies gradually declines as the reservoir of planet-crossing objects is reduced and orbits are cleared or stabilized. What remains is an Earth that still interacts with its cosmic surroundings, yet is no longer dominated by constant catastrophic collisions. The Archean Earth in the young solar system is a world defined by a balance between external delivery and internal processes. The Sun provides light heat and particle streams that control the energy budget and upper atmospheric state. Impactors from the surrounding space add water rock and volatiles while occasionally disturbing the surface. The Moon in a closer orbit shapes tides and contributes to the long-term evolution of the planet's rotation, while its detailed surface expressions belong to the behaviour of the oceans and crust. Against this backdrop, the planet moves forward in its orbital path with conditions at the surface and in the oceans set by the continuous exchange of energy and material between space atmosphere and solid Earth. The Archean atmosphere rests as a continuous envelope over an ocean-covered planet, linking the energy that arrives from the Sun to the heat that leaves from the surface. Its composition and pressure control how much of the incoming light is reflected, how much is absorbed, and how efficiently the planet cools by radiating energy back to space. Volcanic activity, impact delivery, and chemical reactions at the surface all feed gases into this air, while escape to space and reactions with rock slowly remove others. During the early Archean outgassing from a hot interior is intense, so the air likely contains abundant water, vapor carbon dioxide, and smaller but important amounts of other greenhouse gases such as methane. Nitrogen, which is relatively inert, probably makes up a large share of the background atmosphere and contributes to the total pressure without absorbing much infrared radiation. The total surface pressure may be higher than in later times because strong volcanic release and limited loss to space allow gases to accumulate. A higher pressure atmosphere broadens the range of conditions under which liquid water remains stable, widening the gap between the boiling and freezing points at the surface, and making the hydrological cycle more robust. In this setting, sunlight passes through the upper layers of air and reaches the lower atmosphere and surface. Short wavelength ultraviolet radiation is partly absorbed by gases and by hazes made of tiny particles produced when methane and other carbon-bearing gases are altered by high-energy light. These hazes reduce the amount of solar energy that reaches the surface directly, but the greenhouse gases in the lower atmosphere trap much of the outgoing infrared radiation emitted by the warm surface and warm ocean. Even though the young sun emits less total energy than it will in later eons, the strong greenhouse effect keeps the mean surface temperature above the freezing point of water over most of the globe. Regional and temporal variations in cloud cover, volcanic aerosols, and local humidity lead to differences in temperature from place to place and from time to time, but the overall pattern remains one of a warm, wet world. The lower atmosphere in contact with the ocean is thick with water vapor carried upward from the surface. Evaporation from the wide ocean adds moisture to the air whenever liquid water is exposed to warmth and wind. As moist air rises, it cools, causing water vapor to condense into cloud droplets. These droplets grow and merge until they fall as rain back into the ocean or onto exposed land. In some regions, this cycle of evaporation and condensation is rapid and intense with frequent clouds and rainfall. In other regions, subsiding air produces clearer skies and more direct sunlight at the surface. Over Archean timescales, this circulation continually exchanges heat and moisture between the surface and different layers of the atmosphere, moderating extreme temperatures and redistributing energy across the planet. The balance between greenhouse gases is central to this regulation. Carbon dioxide released from volcanoes and from the breakdown of carbon-bearing minerals is a persistent component that spreads widely through the air. Methane produced by high-temperature reactions and later in time by biological processes is a more powerful greenhouse gas per molecule and may accumulate to significant concentrations when destruction by ultraviolet light and oxidation is limited. Water vapor responds quickly to temperature increasing when the surface warms, and decreasing when it cools, which makes it a feedback rather than a primary control. Together, these gases form a radiative blanket that raises the effective emission level of the planet to higher, colder layers, allowing the surface to remain warm. If greenhouse gas levels fall too low, the surface-cooled sea ice may expand from high latitudes, and the reflectivity of the planet increases, which further reduces absorbed sunlight. If greenhouse gas levels rise, the surface warms, sea ice retreats, and darker ocean water absorbs more solar energy. In the Archean, strong internal heat flow and active volcanism tend to maintain comparatively high greenhouse gas inventories, counteracting the faint young sun and keeping average surface temperatures well above the point at which the oceans would freeze solid. Evidence from preserved Archean rock supports the view that liquid water is long-lived at the surface. Certain minerals that form only in the presence of liquid water at moderate temperatures, such as specific types of sedimentary chert and altered basalt, indicate that seawater interacts with the crust rather than remaining locked as ice. Some deposits show features consistent with precipitation from standing water and with transport by flowing water, pointing to a hydrological cycle that includes rainfall, runoff, and infiltration. These geological constraints suggest that while temperatures may at times approach or exceed values that would be considered hot by modern standards, they do not remain at levels that would boil away the oceans on a global scale. Instead, the atmosphere and ocean work together as a coupled system in which water changes phase between vapor-liquid and in limited regions solid, but remains present at the surface through most of Archean time. The vertical structure of the atmosphere also affects how heat and moisture move. Near the surface, a mixed boundary layer responds quickly to changes in heating, developing turbulence as warm air rises and cooler air sinks. Higher up, more stable layers form where temperature decreases more slowly, with height-limiting vertical motion. This structure guides the formation of clouds and the development of weather systems. Although direct details of Archean weather cannot be observed, the same physical laws that govern atmospheric dynamics today apply in this earlier setting given the differences in composition pressure and solar input. Large-scale circulation patterns likely move energy from equatorial regions, where sunlight is strongest toward the poles, smoothing the temperature contrast between low and high latitudes. Seasonal changes in sunlight owing to the tilt of the Earth's axis shift these patterns over the year, altering storm tracks and rainfall distribution across the ocean, covered surface, and scattered land. Over longer intervals, changes in greenhouse gas concentrations, volcanic aerosol loading, and orbital parameters slowly modify the mean climate state, leading to periods that are somewhat warmer or cooler within the overall warm Archean background. The interaction between atmosphere and ocean extends into the chemistry of both reservoirs. Gases dissolve into seawater at the surface, while dissolved species in the ocean can outgas back into the air, depending on temperature and partial pressures. Carbon dioxide enters the ocean and participates in a set of reactions that form bicarbonate and carbonate ions, which in turn interact with dissolved calcium and other metal ions. This exchange links atmospheric carbon to minerals that may precipitate and be buried in sediments. Sulfur-bearing gases emitted by volcanoes dissolve in rain, and seawater forming sulfate and sulfide species that take part in redox reactions with iron and other elements. The overall redox state of the atmosphere during most of the Archean remains reducing to weakly oxidizing with very low free oxygen. In such a setting, iron released from rocks into seawater can remain dissolved at higher concentrations than in later, oxygen-rich oceans, and this in turn affects the colour and opacity of the water and the types of minerals that form when conditions change locally. Through all of these processes, the Archean atmosphere acts as both a physical and chemical mediator between space, the ocean, and the solid Earth. It receives energy from the sun, modulates that energy through scattering, absorption, and re-emission, and returns heat to space at rates set by its composition and structure. It receives gases from volcanoes and from the breakdown of rocks, and delivers them to the ocean and crust while allowing some to escape to space. In return, it is shaped by feedbacks that arise from the presence of liquid water, and from the evolving chemistry of the surface and ocean, yet it continues to support a climate state in which liquid water remains stable over geological timescales. Above the Archean oceans, clouds form and dissipate, rain falls and evaporates, and the air carries the signatures of the planet's interior and its position under a young sun setting. The boundary conditions for all processes that occur at the surface below. The Archean surface sits between the energy of space above and the deep heat of the interior below, and its rocks record the range of temperatures that allow liquid water to persist. The presence of long-lived oceans requires that mean conditions stay within limits where water does not freeze globally and does not boil away, even if local and short-term extremes differ from this average. Because direct observations are not possible, the main evidence comes from ancient rocks that still preserve minerals and textures formed in contact with water at specific temperature ranges. Many of these rocks have been altered by later events, yet careful study reveals signs that constrain the thermal state of the early surface. One important line of evidence is the occurrence of pillow basalts in Archean greenstone belts. Pillow basalt forms when fluid lava erupts underwater and chills rapidly against cold seawater, taking on rounded pillow-like shapes with glassy outer rims and crystalline interiors. The survival of these characteristic structures in Archean sequences indicates that at the time of eruption, liquid water existed at the seafloor, and temperatures that were below the solidification temperature of basaltic lava but also below the boiling point of water at the pressure of the water column. The pillows and their fragmental counterparts, called hyaloclastites, show that the interaction between lava and water was energetic, but did not occur in a purely steam-filled environment, which supports the view of stable, relatively cool ocean water in direct contact with hot rock. Other volcanic and sedimentary rocks point to similar conclusions. Fine-grained volcanic ash layers that settled through the atmosphere into water-produced tuff beds that display graded bedding and wave-reworking features such as ripples and cross-lamination. These structures resemble those formed in later shallow seas and require the presence of liquid water at the surface waves driven by wind and gravitational settling, under conditions where water density and viscosity fall within familiar ranges. The minerals in these tuffs often show alteration by interaction with seawater at moderate temperatures, yielding assemblages of clay minerals and secondary silica that further support the presence of liquid water rather than persistent ice cover. Archean sedimentary rocks provide additional constraints. Bedded cherts, which are silica-rich sediments that can form from the precipitation of dissolved silica in seawater, indicate that extensive volumes of water were saturated with silica derived from volcanic and hydrothermal sources. The textures of some cherts, including lamination and association with stromatolitic structures, show that they accumulated in standing or slowly circulating water bodies rather than in transient meltwater films. The chemistry of these cherts, especially the ratios of oxygen isotopes they contain, has been used to estimate the temperature of the water from which they precipitated. Interpretations of these isotope signals vary, with some studies suggesting relatively warm oceans, and others arguing for more moderate temperatures once later alteration is taken into account. Even with this uncertainty, the data support the existence of liquid water rather than an entirely frozen surface. In addition to cherts, carbonate rocks and their weathering products record information about climate conditions. Archean carbonates, where preserved, can form from the reaction between dissolved carbon species in seawater and calcium or magnesium, leading to minerals such as calcite and dolomite. The formation of these minerals generally requires water that is not extremely hot or extremely cold, and their sedimentary structures such as mud cracks, ripple marks and fenestral textures point to shallow water settings that alternated between submergence and exposure. These features imply a hydrological cycle with rainfall runoff and evaporation, and ground that is firm enough to crack when exposed to air rather than remaining covered by thick ice. Weathering profiles developed on Archean rocks provide a complementary perspective. When rocks at the surface react with water and atmospheric gases, they form characteristic sequences of altered minerals that reflect the temperature and chemical state of the weathering environment. Lateritic profiles, for example, indicate intense chemical weathering under warm, wet conditions, where water percolates through the soil and leaches mobile elements, leaving behind iron and aluminum-rich residues. Some Archean terrains show evidence for such deep weathering, suggesting intervals of high surface temperature and abundant rainfall. In contrast, other areas record more limited alteration, which may reflect cooler or drier conditions, shorter exposure times, or rapid burial. Together, these patterns suggest that Archean climates include both warm intervals and somewhat cooler phases, but they remain within a range compatible with active weathering and flowing water. Another constraint on Archean surface conditions comes from glacial deposits that appear toward the later part of the Eon. Certain sedimentary sequences exhibit features such as diamictites, with striated clasts and striated bedrock surfaces, which in younger rocks are produced by moving ice. These deposits indicate that at least some regions of the planet experience temperatures low enough for glacial ice to form and move likely at high latitudes or high elevations. The presence of such deposits in Archean strata shows that the climate system allows episodes of significant cooling, even while the global mean state remains warm enough to sustain widespread liquid water. The alternation between warmer and cooler intervals can arise from changes in greenhouse gas concentrations, volcanic aerosol loading, continental configuration, and solar output. Yet the geological record does not support an Earth locked permanently in either an extremely hot or entirely frozen state during most of the Archean. The distribution and nature of Archean sedimentary rocks themselves provide a broad indication of surface conditions. Thick sequences of marine sediments, including sandstones, siltstones, shales, and chemical deposits, require long-lived basins that steadily receive material transported by water. Crossbedding channel forms, graded bedding, and other structures point to currents, tides, and storms acting on loose sediments at the seafloor or in shallow water. Subaerial erosion surfaces and unconformities mark intervals when parts of the crust are exposed to the atmosphere and subject to rain rivers and possibly seasonal snow. These features together indicate a dynamic surface shaped by liquid water and gravity rather than by continuous volcanic resurfacing alone. The persistence of these sedimentary records through later deformation and metamorphism suggests that even in a hotter, more active Earth, there are stable windows of time and space where rocks can accumulate and preserve the imprint of surface conditions. Isotopic systems beyond oxygen also contribute to understanding Archean temperatures. Hydrogen isotopes in certain minerals and inclusions can reflect the composition of ancient waters, while silicon isotopes in cherts and other siliceous rocks may carry information about the pathways of silica precipitation and the temperatures of the fluids involved. Sulfur isotopes in sulfide and sulfate minerals record the redox state of the atmosphere and ocean, which indirectly influences climate by affecting the balance of greenhouse gases. These isotopic records are often complex because they can be modified by later heating and fluid flow. But when carefully interpreted, they reinforce the view that Archean surface temperatures span a broad but bounded range, neither approaching a long-term runaway state nor dropping to a permanent global freeze. Across all these lines of evidence, the key point is that Archean rocks record repeated interaction between solid earth and liquid water under conditions that allow a hydrological cycle, weathering, and sedimentation. The surface is sometimes hot, especially near active volcanic centers and in regions of high geothermal flux, and it can be cool enough in certain times and places for ice to form and move. Yet most of the time, the planet maintains conditions that permit extensive standing bodies of water and the continuous exchange of water between ocean atmosphere and land. In this climate framework, early oceans fill low-lying regions. Rain falls from an atmosphere rich in greenhouse gases, and rivers and currents transport sediments that eventually lithify into the very rocks that now serve as records. The Archean surface warmth and liquid water limits are thus written into pillow structures, sedimentary layers, weathering profiles, and isotopic ratios, each preserving a fragment of information about the temperature and state of water at the time of their formation. Together, they show a planet that remains habitable to liquid water over hundreds of millions of years, even as its internal heat and external radiation field continue to evolve. The Archean Earth carries a world ocean that covers most of its surface, with only scattered and relatively low-standing fragments of buoyant crust emerging above sea level. From above, the planet shows wide swathes of water, broken mainly by chains of volcanic islands and small patches of early continental material. The shape and depth of this ocean are controlled by the properties of the underlying lithosphere, the rigid outer shell of rock, and by the high internal heat flow that characterizes this early time. Young oceanic crust, made mostly of basalt, is thin and warm. Warm rock is less dense and more expanded than cool rock, so newly formed seafloor stands at higher elevations and forms broad ridges. As this crust ages and moves away from regions of active magma supply, It cools, contracts, and becomes denser, allowing the seafloor to sink to greater depths. In this way, the ocean basins take shape as large low areas underlain by older cooler lithosphere, while younger crust forms ridges and shallow regions. The depth of water above any point depends on the balance between the height of the solid surface and the total volume of water present on the planet. In the Archean, high heat flow keeps much of the oceanic lithosphere relatively warm and buoyant, compared with later times, which tends to reduce the average depth of basins for a given volume of water. At the same time, frequent volcanic activity builds up local topography on the seafloor, forming seamounts, plateaus, and ridges that rise toward the surface. The result is an ocean floor with strong relief where some regions lie under deep water while others approach or intersect the sea surface as islands or short-lived landmasses. The pattern of ridges and basins is not static. It evolves as magma rises from the mantle, spreads laterally and cools, and as old crust is thickened, buried, or recycled into deeper levels of the earth. Where magma supply is concentrated for long periods, thick sequences of basalt and related rocks stack up to create broad oceanic plateaus that stand higher than average seafloor. These plateaus can modify ocean depth over wide areas and influence currents by reshaping the path of deep and shallow flows. Between them, deeper basins collect water and, over time, sediments. Because the Archean crust is young and the amount of emergent land is limited, the supply of coarse clastic sediment to the deep ocean is smaller than it will be in later eons. Many basins receive thin coverings of volcanic ash, fine mud, and chemical precipitates, rather than thick wedges of sand and gravel. The physical structure of the ocean reflects the distribution of heat at the surface and at depth. Solar energy warms the upper layer, especially at low and middle latitudes where sunlight is strongest and most direct. Wind-driven mixing stirs this layer, creating a surface-mixed zone with relatively uniform temperature and salinity over tens to hundreds of meters. Below this layer, temperatures decrease more rapidly with depth, forming a transition region where water becomes cooler and often denser. At still greater depths, the ocean approaches near uniform temperatures set by long-term contact with the cold sea floor and by mixing along density surfaces. The exact temperature structure is influenced by greenhouse strength heat loss from the crust and the pattern of ocean circulation, but the presence of a stratified water column is a robust outcome of the basic physical conditions. Pressure increases steadily with depth as the weight of overlying water accumulates. This pressure raises the boiling point of water and affects the behavior of fluids rising from the seafloor. Near hydrothermal vents and volcanic centers, water can become very hot without boiling, reaching conditions where it is close to or at the boundary between liquid and vapor states. Even in these specialized environments, however, most of the ocean remains in the liquid state and provides a stable medium for heat and chemical transport on a global scale. Basin geometry strongly influences how water moves. Differences in surface heating, evaporation, and rainfall create contrasts in density that drive large-scale circulation. Warm, relatively low-density water tends to remain near the surface and to move toward higher latitudes, while cooler, denser water sinks and flows along the deep ocean floor. Salinity differences produced by the balance between evaporation, precipitation, and fresh water input from small rivers and subaerial weathering add to these density contrasts. The interaction between wind-driven surface currents and deeper density-driven flows produces a complex pattern of circulation that varies with position and depth, but always respects the shape of the basins and the obstacles presented by ridges and plateaus. Narrow gateways between basins can limit the exchange of water masses, leading to regions with distinct temperature and salinity profiles. Over long intervals, changes in basin shape, caused by vertical motions of the lithosphere alter these pathways and can reorganize circulation patterns. The seafloor itself shows the marks of this dynamic setting. Long volcanic ridges trace out zones of repeated magma upwelling and crust formation. Faults and fracture zones cut across the crust, accommodating differential motion and creating steps and scarps on the ocean floor. In some regions, dense volcanic piles and intrusions cause the crust to sag under their weight, forming deeper centres where sediments accumulate. Elsewhere, uplifted blocks rise, thinning the local water column or even producing temporary land. In the Archean, where internal heat is high and tectonic processes are vigorous, these features may change more rapidly in geological terms than in later eons, yet many basins persist long enough to gather significant thicknesses of sediment and to constrain the pattern of ocean circulation. The distribution of water between shallow and deep regions affects not only circulation, but also the exchange of materials between ocean and crust. On the flanks of ridges and around volcanic edifices, seawater penetrates into the upper crust, through fractures and porous zones becomes heated at depth, and returns to the ocean through focused vent systems or diffuse flow. This hydrothermal exchange alters the composition of the crust and of the water, but the physical setting is defined by the geometry of the basins and the permeability structure of the underlying rocks. In deeper, flatter regions, sediment blankets insulate the crust and can limit direct fluid exchange, while in younger, rugged crust, numerous pathways allow active circulation. The position and depth of basins also determine the volume of water that lies above particular parts of the crust, setting pressure conditions that influence rock deformation and fluid behavior. Over Archean time, the total volume of ocean water is influenced by the balance between sources and sinks. Degassing from the mantle at volcanic centres adds water to the surface reservoirs, while some water is carried back into the interior when hydrated minerals and pore fluids in the crust descend to greater depths during thickening or recycling processes. The relative strength of these fluxes is not known with precision, but the existence of long-lived oceans suggests that they maintain a rough balance on eon timescales. Changes in mean ocean depth may occur as this balance shifts, or as the average elevation of the seafloor changes with cooling of the mantle and thickening of the lithosphere. In the Archean higher mantle, temperatures keep the average seafloor shallower, so for a given water volume the global shoreline sits higher on the crust than it does later, helping to explain the prevalence of broad, shallow marine environments, when buoyant crust rises toward the surface. The early basins are thus the structural framework within which Archean ocean water resides and moves. Their depths and shapes are set by the thermal and mechanical state of the lithosphere. Their history reflects the production, cooling and modification of crust, and their internal relief guides currents and controls sediment deposition. Above them stretches a connected world ocean that spreads heat and mass around the planet, responding continuously to inputs from the interior and from the atmosphere. Within this framework, local environments at the seafloor and in the water column develop their own specific conditions, but all are bounded by the physical constraints imposed by basin geometry and global water volume. The Archean oceans and their basins are therefore central to understanding how water, rock and heat interact on the early Earth, providing the setting for later changes in chemistry and tectonic style that occur further inward in the system. The Archean Ocean is not just a reservoir of water, it is a moving solution of dissolved ions, gases and particles that stays in continuous exchange with the atmosphere, the seafloor and the rocks beneath. Every contact surface between water and solid or gas allows chemical components to enter or leave the seawater, and over long spans of time this exchange shapes the composition of the global ocean. The main solvent is liquid water derived from volcanic degassing and impact delivery, but the solutes come from weathering of rocks, hydrothermal circulation, volcanic ash dissolution, and direct gas exchange across the air-sea interface. Although exact concentrations are uncertain and may vary in space and time, several broad features of Archean seawater chemistry can be inferred from the minerals and chemical signals preserved in ancient rocks. One key aspect is the abundance and behavior of dissolved silica. High rates of volcanic activity and hydrothermal alteration release large amounts of silica into seawater. Hot fluids moving through freshly formed basalt leach silica from the rock, and when these fluids discharge into the cooler ocean, they mix with ambient water and can become supersaturated. Under such conditions, silica precipitates as microcrystalline or amorphous phases that accumulate as chert or as cement in sediments. The widespread presence of Archean banded and massive cherts, particularly in association with volcanic rocks and hydrothermal deposits, indicates that ocean water is often close to silica saturation, and that the flux of dissolved silica from the crust to the ocean is high. In the absence of abundant silica extracting organisms as seen in later times, physical and chemical processes dominate silica removal, allowing relatively high background concentrations to persist. Dissolved iron is another major component that behaves differently under Archean redox conditions than it does in later oxygen-rich oceans. In a largely reducing or weakly oxidizing atmosphere, an ocean ferrous iron remains soluble at higher concentrations, especially in deeper or hydrothermally influenced waters. Fluids exiting seafloor vent systems carry iron and other metals leached from basalt, and these metals mix into the surrounding seawater. When conditions remain, reducing much of this iron stays in solution and can be transported laterally over considerable distances, where localized oxidation occurs, whether through limited chemical reactions in the water column or at the seafloor. Ferrous iron converts to ferric forms and precipitates as iron oxides and hydroxides. These precipitates can settle to the seafloor and contribute to iron-rich sedimentary layers. The coexistence in Archean sequences of iron formation layers, volcanic rocks, and chemical sediments suggests that the ocean holds significant dissolved iron, and that its oxidation and removal are often spatially and temporally patchy, rather than uniform. The major cations, calcium, magnesium, sodium, and potassium, enter the ocean mainly through weathering of crustal rocks and through hydrothermal alteration. Basalt reacts with slightly acidic water, containing dissolved carbon dioxide, releasing these cations into solution. Sodium and potassium remain largely in the dissolved state because they form soluble salts that are not easily incorporated into minerals under typical ocean conditions. Calcium and magnesium, in contrast, can combine with carbonate and other anions to form minerals such as calcite, dolomite, and various silicates. The concentrations of these cations, together with carbonate system chemistry, control the potential for carbonate mineral precipitation. In the Archean, abundant volcanic and hydrothermal activity supplies a large flux of magnesium and calcium, while relatively limited volumes of stable continental platforms may restrict the sites where thick carbonate sequences accumulate. The balance between input and removal determines whether these ions build up in seawater or are drawn down into minerals and sediments. The carbonate system in Archean seawater reflects the exchange of carbon dioxide between atmosphere, ocean, and crust. Atmospheric carbon dioxide dissolves into the ocean at the surface, forming carbonic acid, which partially dissociates into bicarbonate and carbonate ions. The distribution of these species depends on pH temperature and total inorganic carbon concentration. High atmospheric carbon dioxide levels and significant hydrothermal input can produce seawater that is moderately acidic compared with later oceans, with a larger share of dissolved carbon present as bicarbonate and dissolved carbon dioxide rather than carbonate. Under such conditions, carbonate mineral saturation states may be lower, and carbonate precipitation may be more restricted to certain environments, such as shallow warm waters, where degassing evaporation or interaction with reactive substrates drives local supersaturation. The isotopic composition of carbon in Archean carbonate and organic matter provides clues to these processes, but the focus here remains on inorganic exchange. Carbon moves between atmosphere and ocean partitions into dissolved species, and eventually becomes fixed in minerals that can be buried and altered over time. Sulfur chemistry in the Archean Ocean also reflects a balance between volcanic input redox state and mineral formation. Volcanic gases carry reduced sulfur species such as hydrogen sulfide and sulfur dioxide into the atmosphere, where they react with water to form dissolved sulfide and sulfate when they enter the ocean through rain and direct absorption. In a low-oxygen environment, sulfate concentrations in seawater are likely lower than in later eons, and sulfur exists in a mixture of reduced and oxidized forms. Sulfide can precipitate with dissolved iron to form iron sulfide minerals, which accumulate as disseminated grains or as more concentrated layers. Multiple sulfur isotope patterns measured in Archean sulfides and sulfates reveal non-mass-dependent fractionations that are linked to atmospheric photochemical processes under low oxygen conditions, but they also indicate that seawater sulfur passes repeatedly through cycles of reduction-oxidation and mineralization at and below the seafloor. These cycles contribute to the broader redox structure of the ocean and crust even in the absence of pervasive free oxygen. Trace metals such as manganese, copper, zinc and others enter the Archean Ocean through similar pathways, weathering hydrothermal venting and dissolution of volcanic materials. Their solubility and distribution depend sensitively on pH redox state and complexation with ligands in seawater. In reducing conditions, some of these metals remain mobile and can be carried considerable distances in solution, while others precipitate rapidly in association with sulfides or iron oxides when localized oxidation or sulfide availability dictates. The resulting mineral assemblages in ancient hydrothermal deposits, sedimentary exhalative layers, and altered volcanic rocks record these variations and demonstrate that the Archean Ocean is chemically active, with metal fluxes that are closely tied to the thermal and tectonic state of the seafloor. Dissolved gases beyond carbon dioxide also shape seawater chemistry. Nitrogen, mainly in the form of molecular nitrogen exchanges between the atmosphere and ocean, and contributes to the total gas content without participating strongly in inorganic reactions under prevailing conditions. Small amounts of other gases such as hydrogen and methane can dissolve and influence redox balances locally, especially near vent systems or in restricted basins where exchange with the open ocean is limited. Oxygen, when present, likely exists at very low concentrations confined to surface waters or microenvironments influenced by specific chemical or later in time biological processes. Under such low oxygen conditions, many redox-sensitive elements exist in reduced states that differ from those found in later, more oxidizing oceans. The spatial structure of seawater chemistry arises from the interaction between these sources and sinks and the physical circulation of the ocean. Near mid-ocean ridges and volcanic centers, hydrothermal fluids mix with seawater and create plumes enriched in silica metals and reduced species. These plumes rise or spread laterally, depending on their density relative to ambient water, and gradually dilute as they mix. In deep basins, water that is equilibrated with the seafloor at low temperatures may carry a different suite of dissolved species than surface waters that have equilibrated with the atmosphere. Upwelling and downwelling regions driven by winds and density contrasts bring deep waters toward the surface and carry surface waters into the interior, redistributing chemical components throughout the ocean. At the same time, the residence time of many ions in the ocean can be long compared with circulation times, so the global average composition tends toward a steady state, controlled by long-term inputs and outputs. Seawater interaction with the crust proceeds not only through high-temperature vents, but also through lower-temperature circulation in permeable sediments and upper basaltic layers. As water percolates through these materials, it exchanges cations and anions, alters primary minerals to clays and secondary phases, and acquires or loses elements depending on local equilibrium conditions. This process removes some components from seawater, such as magnesium, and adds others such as calcium and silica, helping to regulate ocean composition. Over Archean timescales, repeated cycles of crust formation, hydrothermal alteration, burial and metamorphism act as a global chemical filter through which seawater continuously passes, even though individual water parcels follow complex and varied paths. The chemical state of Archean seawater therefore reflects a dynamic balance. Volcanic and hydrothermal sources add silica metals, carbon, sulfur and other elements. Weathering of emergent crust and volcanic islands supplies additional cations and anions, along with particulate material that can later dissolve or react. Gas exchange at the surface links atmospheric composition to dissolved gases and the carbonate system. Removal processes include mineral precipitation adsorption onto particle surfaces, incorporation into secondary alteration products, and burial of sediments that carry these components into the deeper crust. In this setting, the ocean is neither chemically static nor simple. It is a medium in continual exchange with all solid and gaseous reservoirs it touches. Yet over very long intervals, this continual exchange tends to produce quasi-stable average compositions that leave recognizable imprints in the rock record. Banding in cherts, layering in iron formations, assemblages in hydrothermal deposits, and isotopic patterns in carbon, sulfur and other systems are all expressions of Archean seawater chemistry at the time they form. Through them, it is possible to reconstruct in broad outline an ocean that is rich in dissolved silica and iron, shaped by high hydrothermal fluxes, buffered by extensive interaction with basaltic crust, and set under an atmosphere with high greenhouse gas content and low free oxygen. Within this chemically active body of water, further inward processes at coastlines, volcanic islands, and rising continents operate against a background defined by the composition of the global Archean Sea. Along the margins of the Archean oceans, water meets solid crust in a shifting zone of shorelines, tidal flats, and narrow shelves. These coastlines are controlled by the elevation of the underlying crust, the global volume of seawater, the strength of tides driven by a closer moon, and the local effects of waves and storms generated by the atmosphere. In many places, the coast is not a broad continent edge, as in some later periods, but a relatively steep transition from deep water to shallow water around volcanic islands, short stretches of emergent felsic crust and segments of rugged basaltic plateaus that rise near sea level. The form and behaviour of these margins determine where sediments accumulate, how often areas are exposed or submerged, and how materials from land, sea and atmosphere mix. Because the Moon orbits nearer to the Earth than it does in later eons, its gravitational pull on the ocean is stronger. This stronger attraction produces larger tidal ranges, especially in embayments and along irregular coastlines, where the geometry of basins can amplify the motion of water. Twice during each lunar day, water levels rise and fall, driving strong tidal currents through narrow straits and across shallow platforms. In some settings, the difference between high and low tide can be many meters enough to expose wide areas of seafloor at low tide and to flood them at high tide. The interplay between lunar tides, solar tides, and local resonance within inlets and bays creates patterns of currents that shift in strength and direction over the tidal cycle. These currents reshape sediments, transport suspended particles, and influence the distribution of chemical gradients in coastal waters. Wind-driven waves act together with tides to sculpt the shoreline. Over the open ocean, winds blowing across the water surface generate waves that travel long distances before breaking in the shallow zone near land. Where coastlines are steep and rocky, waves strike directly against exposed lava flows, fractured basalts, and early felsic outcrops, eroding them mechanically and chemically. Blocks and fragments fall from cliffs, and fine particles are abraded into sand and silt that move along the shore under the combined action of waves and currents. Where the coast is low and gently sloping waves dissipate their energy over broader shallow areas, stirring the upper layer of sediments and maintaining beds of mobile sand and mud. Coastal geometry, including the presence of headlands, embayments and offshore ridges, focuses wave energy in some places and shelters others, creating a patchwork of high energy and low energy environments within relatively short distances. The distribution of these energy conditions exerts a strong control on the types of sedimentary structures that form. High-energy shorelines display coarse lag deposits of pebbles and cobbles, scoured surfaces and cross-bedded sands produced by migrating bars and channels. Lower-energy tidal flats and sheltered bays accumulate finer-grained muds that settle from suspension during slack water. As tides rise and fall, these flats alternate between submergence and exposure, allowing surfaces to dry crack and then be flooded again. Repeated cycles of inundation and emergence create characteristic patterns, such as mud cracks, ripple marks, and wrinkle structures that can be preserved when sediments are buried and lithified. In some places, chemical sediments also form in coastal settings. Evaporation in restricted lagoons and tidal ponds can concentrate dissolved ions, promoting the precipitation of minerals such as carbonates or, under appropriate conditions, salts. The rate of evaporation depends on temperature, humidity, and wind, while the chemical outcome depends on the composition of incoming seawater and any freshwater input from small streams or groundwater. Although large continental rivers are less common in the Archean small drainage systems on volcanic islands, and emergent continental fragments still deliver dissolved and particulate material to the coast, creating local variations in salinity and chemistry that can favour particular mineral assemblages. The proximity of active volcanism to many Archean coastlines further complicates these environments. On volcanic islands and oceanic plateaus that stand near sea level, eruptions may occur close to or even within the coastal zone. Lava flows can enter the ocean, cooling rapidly and breaking into fragments of glassy debris that accumulate as hyaloclastite deposits along the shore and in adjacent shallow basins. Explosive eruptions send ash and lapilli into the atmosphere, some of which falls into the sea, and some onto land from where it can be reworked by waves and currents. These volcanic materials are prone to rapid alteration when exposed to seawater and to the air, releasing cations and silica that modify coastal water chemistry and providing unstable grains that can transform into secondary minerals during early diagenesis. The mechanical and chemical erosion of volcanic rocks along Archean shores produces distinctive sediment suites. Basaltic and komatitic rocks weather into mixtures of sand-sized fragments, volcanic lithic grains and mineral particles such as pyroxene olivine and plagioclase. Under warm, wet conditions, these minerals break down further to form clay minerals and iron-rich residues which are then transported to the coast by short rivers and surface runoff. On felsic fragments of crust, weathering yields quartz, rich sands and feldspar that can accumulate in nearby coastal basins. The relative proportions of volcanic and felsic sediment at any given coastline depend on the composition and age of the underlying crust. But in many Archean environments, volcanic sources dominate. Sediments deposited along these coasts record not only the physical processes of waves and tides, but also the chemical interactions between seawater and freshly exposed rocks. Tidal channels cut into coastal plains, guiding water back and forth between open ocean and shallow interior embayments. During flood tide, marine water carries suspended particles and dissolved components landward. During ebb tide, water returns seaward, often with a different load. Over time, these bidirectional flows build complex channel networks and bar forms. Sedimentary structures such as herringbone cross-stratification flazer and lenticular bedding and inclined heterolithic stratification can develop under such conditions, encoding the alternation between opposing currents and varying sediment supply. When these deposits are later buried and preserved, they provide detailed records of tidal dynamics and coastal morphology in the Archean. Coastal subsidence and uplift driven by the loading and unloading of sediments, magmatic intrusions and deeper crustal motions cause shorelines to migrate laterally over geological timescales. Where the crust subsides, relative sea level rises locally, allowing marine conditions to move landward and deepen. This transgression leads to vertical successions in which coastal and shallow marine sediments overlie older terrestrial or nearshore deposits. Conversely, when uplift occurs, relative sea level falls locally and the shoreline moves seaward. Regressive sequences show shallow marine and coastal sediments overlain by more terrestrial or emergent faces, sometimes capped by unconformities representing periods of non-deposition or erosion. In the Archean, with high internal heat and active tectonics, these vertical and lateral shifts may be more frequent or pronounced than in some later periods, yet the basic patterns of transgression and regression still apply, tying coastal stratigraphy to the vertical motion of the crust. Tides and waves also influence the distribution of early chemical gradients at the land-sea interface. Mixing of oxygen, poor seawater with fluids that have interacted with the atmosphere or with weathered rocks can create zones where redox conditions change over short distances. In such zones, iron, manganese, sulfur and other elements may change oxidation state and precipitate as distinct mineral phases. For example, where reduced iron-bearing water encounters more oxidizing conditions in shallow coastal settings, iron oxyhydroxides can form and settle as thin layers or as coatings on grains. Where reduced sulfur is present, iron sulfides can precipitate in muddy sediments. The vertical arrangement of these minerals in coastal deposits reflects the position of the redox boundary relative to the sediment-water interface, which can shift with changes in water depth, energy regime and sedimentation rate. Even without focusing on biological activity, these geochemical transitions represent important features of coastal Archean environments. Over very long timescales, the cumulative effect of erosion sediment transport and deposition along Archean coastlines contributes to the gradual growth and modification of early crustal fragments. Material removed from emergent rocks by wave attack and subaerial weathering is redistributed into adjacent basins where it may be buried and incorporated into the shallow crust. Repeated cycles of uplift, erosion and deposition recycle this material, increasing the heterogeneity of the upper crust and creating layered packages of sedimentary and volcanic rocks that can later be deformed and metamorphosed. The narrow but dynamic zone where ocean meets land is therefore a key site of material transfer, linking the mechanical energy of tides and waves to the long-term construction of crustal architecture. Along the Archean shore, all these processes operate under a sky shaped by a greenhouse-rich atmosphere and a strong lunar tide generating force producing coastlines that are physically energetic and chemically active. Their exact forms vary from place to place, but they share common controls: the elevation and composition of the underlying crust, the configuration of nearby basins, the strength of tides from a closer moon, and the impact of wind-driven waves and storms. Within this coastal belt, sediments, dissolved substances, and rock fragments are mixed, sorted and buried in patterns that will later serve as detailed records of how the first stable oceans interacted with the rising edges of early land. Beyond the immediate surf zone, the Archean oceans spread into broad tracts of shallow water where waves, tides and currents act on the seafloor, but do not reach the great depths of the open basins. These shallow seas form over uplifted portions of oceanic plateaus around volcanic island flanks, and above early fragments of buoyant crust that sit only a few tens to a few hundreds of meters below sea level. In such water depths light can penetrate to the seabed. Waves can stir the sediment during storms, and tidal currents can move material back and forth across the bottom. These conditions create a spectrum of environments that range from high-energy shore face to quieter offshore shelves, and they produce sedimentary layers that preserve the physical and chemical state of the Archean surface. Near the shore in the upper shore face, fair weather waves repeatedly rework sand and coarser grains. The constant motion sorts particles by size and density, winnowing finer material offshore and leaving better sorted sands nearer the beach. Crossbeds, which are inclined layers formed by the migration of underwater dunes, and ripples develop as waves and longshore currents push sediment along the seafloor. During storms, larger waves generated over wide stretches of ocean penetrate deeper, reaching into areas that are normally less disturbed. At these times, sediment is eroded from shallower zones and carried offshore, then deposited as the storm wanes. This alternation between fair weather and storm conditions creates characteristic successions in which more massive structureless or hummocky layers formed during storms alternate with more laminated strata formed during calmer intervals. Further from shore in the lower shore face and outer shelf, the energy of ordinary waves is reduced at the seabed, and only the larger storms disturb deeper layers. In these settings, fine sand, silt and mud settle from suspension between high-energy events. Currents associated with tides and density contrast can still reshape the bottom, but the net effect is typically the accumulation of finer-grained, more continuous beds. The presence of combined flow ripples, low-angle cross-lamination, and subtle graded bedding in some Archean sequences points to such mixed energy conditions where both oscillatory wave motion and directional currents operate. The exact pattern at any location depends on water depth, exposure to storms, tidal range, and the supply of sediment from nearby land and volcanic sources. Tidal flats and lagoons occupy more sheltered parts of the shallow seas, often behind barrier complexes or in embayments adjacent to emergent crust. In these areas, water depth can change markedly over a tidal cycle, and large areas of seabed can be exposed at low tide. Sediments here are dominantly fine-grained muds and silts, interbedded with thin layers of sand brought in during stronger flows. The repeated wetting and drying of surfaces leads to the development of desiccation cracks, which open when water evaporates and close partly when sediments are flooded again. These cracks may later fill with new sediment, producing polygonal patterns in cross-section. Ripple marks on these surfaces record the direction and strength of currents during individual episodes of submergence. In some Archean tidal flat deposits, irregular microtopography and thin cohesive layers suggest the presence of microbial mats that stabilize the sediment surface and modify small-scale hydrodynamics. Their physical influence on sediment trapping and binding helps to produce laminated structures that are resistant to erosion, contributing to the preservation of fine details in the rock record. Sediment supply to the shallow seas comes from several sources. Volcanic islands and plateaus deliver large volumes of loose pyroclastic material lava fragments and chemically weathered products into adjacent waters. Ash falls settle through the water column, forming tuff layers that can be reworked by waves and currents into bedded deposits. Hyaloclastite debris produced where lava enters the sea accumulates at the base of coastal slopes and can be redistributed onto nearby shelves. These volcanic-derived materials are typically rich in unstable minerals that alter rapidly when in contact with seawater, generating clay minerals, iron-rich phases and silica that further influence seawater chemistry and early diagenesis. Emerging felsic crust where present contributes quartz, rich sands and feldspathic material that can accumulate in local basins and on shelves, bordering early continental fragments, but the overall dominance of mafic rocks in Archean settings means that many shallow sea sediments have compositions that reflect basaltic sources. Chemical sediments form alongside clastic deposits in these shallow marine environments, where seawater becomes supersaturated with respect to carbonate minerals. Calcium and magnesium carbonates precipitate on the seafloor or within the upper layers of sediment. This can occur in warm, shallow waters where evaporation is significant, where carbon dioxide degasses to the atmosphere, or where interaction with reactive substrates locally increases pH and carbon ion concentration. The resulting carbonate deposits range from mud-grade accumulations to granular or stromatolitic buildups, depending on the interplay between precipitation sediment supply and physical reworking. Silica may also precipitate within shallow seas either directly from solution or by replacement of earlier carbonate and mud deposits forming chert layers and nodules. Iron present in dissolved form in seawater, especially under reducing conditions, can precipitate as iron oxyhydroxides when redox conditions shift toward more oxidizing values in the upper water column or at the sediment-water interface. In shallow settings where mixing with more oxidized waters or exposure to the atmosphere is possible, thin iron-rich laminae can accumulate, sometimes forming the shallower parts of iron formation successions. The stacking of sediments in shallow Archean seas reflects the combined effects of relative sea level change, sediment supply rate and subsidence of the underlying crust. Where subsidence and sea level rise outpace sedimentation, water depths increase with time, and a vertical succession records a transition from coastal or tidal flat deposits to more offshore, finer-grained facies. Mudstones may overlie sandstones, and structures indicative of frequent exposure give way upward to those formed entirely under subaqueous conditions. Where sediment supply keeps pace with or exceeds accommodation, shallow water conditions can persist over long intervals, and thick packages of shore face and shallow shelf deposits build upward. In some cases, progradation occurs with shoreline and shallow faces advancing seaward over deeper water deposits, leaving a record of coarsening upward sequences as more proximal environments shift over a given location. These patterns are controlled by local tectonic behavior because uplift or accelerated subsidence of blocks of crust can alter water depth independently of global seawater volume. Early diagenesis. The suite of changes that occurs as sediments are buried and begin to lithify is particularly active in Archean shallow marine deposits because of high heat flow and abundant reactive components. As sediment piles thicken, pore waters become isolated from the overlying ocean and evolve in composition as minerals dissolve and precipitate. Compaction expels water, aligns grains and reduces porosity. Carbonate and silica cements grow in pore spaces, binding grains together and converting loose sediment into rock. Chert nodules and layers can form by replacement of pre-existing material, preserving or obscuring original sedimentary structures depending on the pace and style of replacement. In some settings, magnesium-rich fluids modify original carbonate minerals, leading to dolomitization and the formation of dolostone with distinct textures. Iron sulfides and oxides precipitate within sediments, where redox conditions favour their stability, producing disseminated grains or thin laminae that contribute to the overall geochemical signature of the sequence. These diagenetic processes are not uniform. They vary with depth, temperature, composition of pore fluids and time, but they share a common role in transforming soft water, rich sediment into solid rock that can survive subsequent tectonic and metamorphic events. The physical arrangement of facies in Archean shallow sea successions offers clues to the geometry of early platforms and shelves. Laterally continuous beds of similar thickness and composition suggest broad, gently sloping depositional surfaces, whereas abrupt facies changes over short distances can indicate irregular topography, such as fault-bounded blocks or volcanic edifices. In some areas, thick accumulations of shallow marine sediment drape older volcanic piles, recording a transition from a dominantly volcanic landscape to one where sedimentation becomes more important. In others, relatively thin, discontinuous shallow sequences are interbedded with volcanic flows, and intrusions showing that sedimentation occurs contemporaneously with ongoing magmatic activity. Over long intervals, the repeated development of shallow seas over particular regions indicates that these crustal blocks remain near sea level despite the active tectonic environment, suggesting some degree of buoyant support or crustal thickening. Shallow Archean seas thus occupy an intermediate position between the high-energy coastal zone and the deeper basins. They are sites where physical processes such as waves, tides, and storms work together with chemical processes such as carbonate and silica precipitation and redox-driven mineral formation to build layered sequences of sediment. These sequences record water depth energy regime sediment sources and evolving seawater chemistry. Once lithified, they become key components of the Archean rock record found today in greenstone belt successions and in the margins of early cratonic blocks, preserving the history of how sedimentary systems operated on a planet with high internal heat, limited but growing land areas and extensive long-lived oceans. In these shallow marine settings, water rock fragments and dissolved components interact continuously, creating the materials and structures that will underlie later stages of crustal growth and tectonic organization. Rising above the Archean oceans, chains of volcanic islands and elevated plateaus mark places where magma from the mantle reaches the surface and builds new crust. These islands sit along zones of focused magmatic activity, such as long linear ridges and more localized hotspots, and they form one of the most visible expressions of the restless state of the early lithosphere. Their foundations are made mostly of basalt, and in some places ultramafic rocks rich in magnesium and iron. Over time, repeated eruptions construct steep volcanic cones, overlapping lava flows and broad shield-like edifices that may stand thousands of meters above the surrounding seafloor and hundreds to more than 1,000 meters above sea level. The shapes of these islands and plateaus reflect the viscosity of their lavas, the rate and style of eruptions, and the way they interact with water and atmosphere. At depth, partial melting in the mantle produces magmas that rise because they are less dense than the surrounding solid rock. These magmas ascend through fractures and weak zones, pooling in reservoirs within the lower and middle crust, before continuing upward. In the Archean high mantle, temperatures and strong convection favour the production of magmas that are hotter, and in some cases more magnesium-rich than those common in later times. Komatitic magmas, which are especially rich in magnesium and have very low viscosity at eruption temperatures, are characteristic of this period. When these magmas reach the surface in submarine or subaerial eruptions, they flow rapidly and can travel long distances from their vents, forming sheet-like or channelized flows that wrap around existing topography. Basaltic magmas, also abundant, produce a range of eruptive forms, from gentle effusions to explosive events, depending on gas content and interaction with water. Where eruptions occur beneath the ocean surface, the immediate contact between hot magma and cold seawater causes rapid quenching and fragmentation. Submarine basaltic eruptions typically form pillow lavas, which are rounded masses of solidified lava with glassy outer skins enclosing more crystalline interiors. These pillows stack and interlock to build the submarine flanks of volcanic islands and oceanic plateaus. In more explosive submarine eruptions, magma is fragmented into ash and lapilli-sized pieces that accumulate as breccias and tuffs, often with complex internal structures reflecting repeated pulses of activity and interaction with water. Komatitic eruptions can produce very thin, rapidly emplaced flows that cool from the top and bottom inward, sometimes preserving characteristic spinifex textures formed by large skeletal crystals of olivine. These flows can drape submarine slopes, and where they erupt in shallow water or emerge above sea level, contribute to the visible morphology of islands. As volcanic edifices grow, they may emerge above sea level to form subaerial volcanoes. On land, lava flows can spread more freely without immediate quenching by water, although rainfall and surface water still influence cooling and erosion. Successive eruptions build overlapping layers of lava and pyroclastic material, producing stratified volcanic piles with complex architecture. Conduits and dikes cut through earlier rocks, feeding new flows and intrusions. Flank collapses driven by gravitational instability and weakening of rocks by alteration can remove large portions of volcanic edifices and send mass flows of debris into the surrounding ocean. These collapse events reshape island topography and create thick deposits of volcanic breccia and conglomerate along the submarine slopes. The interaction between volcanic islands and the surrounding ocean is continuous. Waves and tides attack the flanks of islands, undermining cliffs and reworking loose material. Shorelines retreat landward over time as erosion removes rock and supplies sediment to adjacent shallow basins. Chemical weathering in the warm, humid Archean climate transforms primary volcanic minerals into clays and iron. Rich residues, especially on the upper parts of islands where rainfall is concentrated. Water percolating through porous lava flows leaches mobile elements and deposits secondary minerals in voids and fractures. These processes weaken rock masses, making them more susceptible to mechanical erosion and mass wasting. The eroded material is transported downslope by gravity-driven flow surface runoff and submarine density currents, contributing to the sedimentary infill of nearby basins. Hydrothermal systems are common within and around Archean volcanic islands. Seawater penetrates through fractures into the hot interior of the volcanic pile, where it is heated by contact with magma bodies and still warm intrusions. As the water warms, it reacts with the surrounding rocks, dissolving metals and altering primary minerals to chlorite, epidote, and other secondary phases. When the heated buoyant fluid becomes sufficiently overpressured or finds pathways back to the seafloor, it discharges through vents as hydrothermal plumes. These vent fluids, often rich in silica, iron, manganese, and other metals, mix with cooler seawater, precipitating mineral particles that settle to the seafloor or remain suspended and travel with currents. On the slopes of volcanic islands and in nearby basins, hydrothermal deposits accumulate as layers of iron-rich sediments, manganese-rich crusts, and sulfide mineralization where reduced sulfur is present. These hydrothermal systems represent key sites of chemical exchange between the interior and the ocean, but their physical existence depends on the permeable volcanic foundations and the presence of heat sources within growing islands. The internal structure of volcanic islands and oceanic plateaus is complex. At depth, networks of dikes and sills thread through the crust, connecting deeper magma sources to surface vents. These intrusions can thicken and strengthen the crust, locally creating zones of higher rigidity that influence subsequent deformation. Above sequences of lava flows breccias and tuffs stack to form packages that may reach several kilometers in thickness. The density contrast between these volcanic piles and the underlying mantle and lower crust determines how much they subside under their own weight and how they interact with broader tectonic motions. In some cases, the accumulation of thick volcanic sequences leads to flexural bending of the lithosphere, forming peripheral basins that trap sediment shed from the central edifice. Over time, subsidence can partially or completely submerge earlier subaerial parts of the island, turning them into shallow marine platforms or fully submerged seamounts. In the Archean, where heat flow is high and the lithosphere is comparatively thin, The evolution of volcanic islands and plateaus may proceed more rapidly than in later eons, with faster cycles of growth, subsidence, and burial. Deformation associated with larger-scale tectonic processes also affects these volcanic constructs. Compression extension and lateral shearing within the lithosphere can tilt fold-and-fault volcanic sequences, altering their original geometry. Greenstone belts observed in ancient cratons often preserve deformed volcanic and sedimentary rocks that once formed oceanic plateaus and island arcs. In such belts, steeply dipping volcanic flows and pillow lavas interlayered with sediments attest to substantial tectonic reworking after initial emplacement. Shear zones may cut through these sequences, mixing different rock types and obscuring the original relationships between volcanic centers and their surroundings. Even so, detailed mapping and structural analysis allow reconstruction of the early stages when these rocks formed constitutive parts of Archean volcanic islands and plateaus. The chemistry of volcanic rocks erupted on Archean islands provides insight into their mantle sources and the conditions of magma generation. Basalts typically exhibit signatures consistent with melting of a mantle that is hotter and in some regions less chemically depleted than typical modern mantle. Komatiites require especially high degrees of partial melting at high temperatures, conditions more likely when the mantle is significantly hotter. The presence and distribution of these rock types in Archean volcanic sequences indicate that mantle plumes or upwellings may be common, delivering large heat and material fluxes to the base of the lithosphere. Variations in trace element and isotopic compositions within volcanic suites reveal differences in source composition, degrees of melting and crustal contamination, showing that even in this early time the system exhibits spatial and temporal complexity. Volcanic gases released during eruptions are a major source of volatiles to the Archean atmosphere. Water vapor, carbon dioxide, sulfur, bearing species and smaller amounts of other gases escape from magmas as they rise and decompress. On islands, these gases discharge both during explosive activity and through more diffuse fumarolic venting. When released into the atmosphere, they contribute to greenhouse warming cloud formation and the global sulfur and carbon cycles. When dissolved directly into seawater near submarine vents and shallow eruptions, they influence local pH and redox conditions, altering the chemistry of surrounding waters. The balance between gas-release dissolution and atmospheric processing sets the contributions of volcanic islands and plateaus to the broader climate and chemical environment of the Archean Earth. Over geological timescales, the life cycle of a volcanic island proceeds through stages of growth, stability, and decay. Growth occurs during periods of active magmatism, when new flows and pyroclastic material add mass and height. Stability follows when magma supply wanes, and erosion begins to dominate over constructive processes, lowering relief and smoothing topography. Decay advances as erosion and subsidence reduce islands to low-lying remnants, or fully submerged seamounts, which may become sites of carbonate or other sediment accumulation. In the Archean, this cycle is superimposed on rapid tectonic change, so individual islands and plateaus may be swept into zones of deformation, buried beneath younger crustal additions, or thickened into deeper structural levels of emerging crustal blocks. Some remnants are preserved in relatively coherent belts, while others are broken into smaller fragments within complex metamorphic terrains. Despite these later modifications, the original role of volcanic islands above restless crust remains central. They are primary sites of mantle material reaching the surface of heat and chemical fluxes into the oceans and atmosphere, and of early crustal construction that will, after further processing, contribute to the formation of more stable, buoyant continental fragments. As such, Archean volcanic islands link the convecting mantle to the surface hydrosphere, converting deep thermal and compositional gradients into observable structures of lava ash and altered rock that stand above the surrounding ocean and slowly change with time. In the Archean oceans, some regions of the seafloor rise well above their surroundings as thick accumulations of basalt and related rocks build broad oceanic plateaus. These plateaus differ from ordinary oceanic crust in both thickness and composition. Instead of a few kilometers of basalt formed by moderate degrees of partial melting at spreading centers, plateau crust can reach several times that thickness produced by higher melt fractions and sustained magmatic activity often linked to mantle plumes or other zones of focused upwelling. At depth, hot mantle rises toward the base of the lithosphere and begins to melt when the pressure and temperature conditions cross the solidus. Because the Archean mantle is hotter than at later times, the volume of melt generated in such upwellings can be large, and melting may extend over a greater vertical distance. The resulting magmas are dominantly basaltic with locally abundant ultramafic compositions, where degrees of melting are especially high. These magmas ascend pond and spread, forming thick stacks of lava flows and intrusive bodies that thicken the oceanic crust and elevate the seafloor over broad areas. At the surface, plateau-building eruptions can be both submarine and where the edifice rises sufficiently subaerial. Submarine eruptions produce pillow lavas and volcanic breccias that accumulate rapidly on the seafloor, burying older crust and smoothing previous topographic lows. When the plateau top approaches or crosses sea level, lava flows may spread laterally in shallow water or on land, forming sheet flows and compound flow fields with low slopes. The repeated emplacement of such flows creates a vertical succession of mafic rocks that can reach many kilometers in thickness. Interlayered within these volcanic units are intervals of volcaniclastic sediment, ash fall deposits, and chemical sediments precipitated from seawater, all of which record pauses or changes in eruptive activity and variations in the local depositional environment. The architecture of an Archean oceanic plateau is therefore a complex arrangement of flows, breccias, tuffs, and intrusions built over relatively short geological intervals by high magma flux. As the volcanic pile thickens, its weight causes the underlying lithosphere to flex and subside. This subsidence creates space for more sediment and volcanic material to accumulate and can drown previously shallow areas, turning emergent or near-surface portions of the plateau into deeper water environments. Peripheral basins develop around the edges of the plateau where flexural bending is greatest. These basins receive sediments eroded from the plateau surface, along with volcanic material from ongoing eruptions and chemical precipitates from seawater. The combination of central uplifted areas and flanking basins produces a varied topography that influences ocean circulation and sediment pathways. Water masses flow around and over the plateau, while gravity-driven density currents transport sediment downslope into deeper parts of adjacent basins. Hydrothermal circulation is particularly intense in and around oceanic plateaus. The thick volcanic pile is highly fractured and permeable, especially in its upper portions, and magma chambers and dikes provide strong local heat sources. Seawater penetrates into these rocks, warms as it descends toward hot zones, reacts with primary minerals, and then rises as buoyant chemically altered fluid. Where these fluids reach the seafloor, they discharge through focused vents and diffuse flow fields, releasing heat and dissolved components into the overlying ocean. Iron, manganese, silica, and a range of trace metals are abundant in such hydrothermal outputs, and they precipitate in part as mineral particles when mixing with colder seawater, changes temperature and redox conditions. On the plateau surface and its flanks, these hydrothermal products accumulate as layers of iron-rich sediment, manganese oxides, and silica-rich deposits that can later be transformed into banded iron formations, manganese-rich units, and cherts. The continuous interaction between seawater and the thick basaltic crust of the plateau therefore plays a major role in setting the chemical environment of the surrounding ocean. The internal layering of oceanic plateaus often includes ultramafic flows and cumulate bodies at the base overlain by more typical basaltic sequences and capped by volcanic lastic and sedimentary units. Komatiitic flows with their low viscosity and high eruption temperatures can form at early stages in plateau growth, when mantle temperatures and melt fractions are at their highest. These flows may pond in low areas or spread as thin, laterally extensive sheets. Above them, more evolved basalts erupt as melting conditions change, and the mantle source becomes progressively depleted. Over time, the volcanic activity wanes, and sedimentation becomes increasingly important on the plateau surface. The resulting stratigraphy contains upward transitions from ultramafic to mafic lavas, through mixed volcanic and sedimentary units, into more purely sedimentary successions that reflect a shift from construction by magma to modification by surface processes and oceanic deposition. The later geological record preserves many of these plateau-derived successions as greenstone belts in ancient cratons. In these belts, originally horizontal or gently dipping volcanic and sedimentary layers are tilted, folded and faulted by subsequent tectonic events, but their internal sequences still reflect their origin on thickened oceanic crust. Typical greenstone belt successions show lower units of pillow lavas and komatiitic flows, overlain by massive basalts, volcanic lastics and chemical sediments such as cherts and iron formations with finer grained sediments higher up. This arrangement is consistent with early plateau volcanism, followed by progressive subsidence and sedimentation. Although deformation and metamorphism alter mineral assemblages and structures, careful field and petrographic observations reveal features such as preserved pillows, spinifex textures and volcanic lastic bedding that point back to their volcanic and oceanic origins. The mechanical behaviour of oceanic plateaus under Archean tectonic stresses differs from that of thin oceanic crust. Their greater thickness and buoyancy can make them more resistant to complete recycling into the mantle, and more likely to be preserved and incorporated into longer-lived crustal fragments. When lateral forces compress, the lithosphere plateaus can act as strong blocks that focus deformation into surrounding weaker regions. They can also collide with other plateaus or with emerging areas of more felsic crust, leading to complex zones of thickening, stacking and shearing. During such events, volcanic and sedimentary sequences are folded and faulted, forming the characteristic structural fabric seen today in greenstone belts. Strong deformation can juxtapose rocks that originally formed at different depths and in different parts of the plateau system, obscuring original spatial relationships, but recording the intense tectonic reworking that follows their initial emplacement. Metamorphism overprints plateau and greenstone sequences as they are buried to greater depths. Under green schist to amphibolite facies conditions, primary basaltic and ultramafic minerals such as olivine, pyroxene and plagioclase transform into assemblages of chlorite, actinolite, amphibolate, epidote and other minerals typical of greenstone rocks. Komatiites develop distinctive mineralogies that still reflect their high magnesium content, while pillow structures and volcanic textures may remain partly recognizable. Chemical sediments, including cherts and iron formations, recrystallize into interlayered quartz iron oxides and related minerals when present, preserving their banded appearance. Despite these transformations, the overall composition and layered nature of the sequences continue to reflect their origin as thick volcanic and sedimentary successions built on oceanic plateaus. The development of plateaus also affects the heat budget of the lithosphere. Thick volcanic piles insulate the underlying mantle and lower crust, slowing cooling compared with thinner crust. They also store magmatic heat within their intrusive components. Over time, as radioactive decay and loss of primordial heat reduce mantle temperatures, the relative importance of plateau building may decline. But in the Archeans, these structures represent major conduits for heat loss from the deep earth. Their presence modifies regional geothermal gradients, influencing the style and extent of metamorphism in adjacent rocks and the conditions of subsequent deformation. As the mantle gradually cools, the characteristics of partial melting change, leading to shifts in magma composition and volume that are reflected in the volcanic stratigraphy of successively younger plateaus. The erosional history of oceanic plateaus and their preserved greenstone counterparts is also significant. Once magmatic construction slows and subsidence lowers plateau surfaces deeper into the ocean, physical erosion at the surface decreases and chemical weathering becomes more limited. Sedimentation dominates, burying older volcanic surfaces under layers of mud, sand, and chemical deposits. Later, when tectonic processes uplift these sequences into the upper crust of growing cretonic regions, they enter the weathering regime at the surface, and erosion exposes cross-sections through their stratigraphy. Modern outcrops in Archean cratons often show vertical slices through ancient plateaus, allowing present-day observers to trace transitions from basal ultramafic units through thick basalt piles into overlying sediments. These windows provide direct evidence for the role of oceanic plateaus as precursors to the greenstone belts that fringe and penetrate stable continental cores. Throughout their life cycles, Archean oceanic plateaus and their volcanic products participate in the ongoing exchange of material between mantle crust and ocean. They represent zones where large volumes of mantle-derived melt reach the surface and solidify, where seawater circulates deeply into hot rocks and returns laden with dissolved substances, and where sediments accumulate in basins shaped by flexure and subsidence. Their thick, mafic-dominated crustal sections are among the earliest substantial additions to the lithosphere that can later be preserved and reworked into more complex crustal provinces. By building elevated regions of oceanic crust and providing the raw material for greenstone belts, these plateaus help define the physical and chemical framework within which the next inward step of crustal evolution takes place, as buoyant, more silica-rich rocks begin to assemble into the first enduring fragments of continental crust. As Archean oceanic plateaus and volcanic arcs thicken and cool parts of the crust begin to undergo transformations that produce rocks with higher silica content and lower density than the surrounding mafic and ultramafic material. These lighter rocks, dominated by tonalite trondiamite and granodiorite, form what is often called felsic crust. Their emergence marks a key change in the character of the planet's outer shell, because such crust can stand higher above the underlying mantle and ocean basins than ordinary basaltic crust. The formation of these rocks requires specific conditions of pressure, temperature, and water content. Basaltic crust that has been hydrated at the surface or in the upper oceanic crust through interaction with seawater and hydrothermal fluids can be carried to greater depths by processes that thicken or bury it, such as underplating, by new magmas, stacking of crustal slices, or sinking of dense sections into hotter regions of the lower crust or upper mantle. As this hydrated mafic material warms under increasing pressure, some minerals begin to melt while others remain solid. The resulting partial melts are richer in silica and sodium than the original rock, and have lower density, so they separate from their residue and rise towards shallower levels. When these melts crystallize, they form tonalite trondhjemite granodiorite bodies that are more buoyant than the mafic and ultramafic rocks around them. Over time, repeated episodes of partial melting and melt extraction can build up significant volumes of felsic material within the upper crust. The Archean environment, with its high internal heat flow and abundant mafic crust, provides many opportunities for such processes. Thick oceanic plateaus, arcs, and crustal piles, subjected to continued magmatic underplating and tectonic thickening, develop zones at depth where temperatures are high enough and water content sufficient to initiate melting. In some cases, dense lower crustal sections rich in garnet and iron sink, further leaving behind lighter silica-rich rocks. In others, rising mantle-derived magmas stall in the lower crust and transfer heat to surrounding rocks, driving partial melting there. The outcome is the gradual concentration of felsic material in certain regions of the lithosphere. These zones of light crust can then buoyantly rise or remain at relatively high structural levels compared with adjacent mafic domains forming the cores of early continental fragments. At the surface, these fragments appear as irregular areas of higher standing crust surrounded by lower elevation mafic terrains and ocean basins. Their sizes vary from small blocks only tens of kilometers across to larger complexes that extend over hundreds of kilometers. Many are not continuous land masses. Instead, they may be archipelagos of island-like highs linked by shallow submerged platforms. The exact amount of emergent land depends on the balance between crustal thickness, isostatic support, and global sea level, but these felsic fragments tend to rise higher than surrounding basaltic plateaus for a given thickness, because their average density is lower. Where they stand above sea level, they participate directly in weathering and erosion under the Archean atmosphere, supplying sediments to adjacent shallow seas. Even where they remain just below sea level, they influence patterns of sedimentation and ocean circulation by providing broad, relatively stable platforms. The internal architecture of these early continental fragments is complex and reflects both their magmatic origins and subsequent deformation. Deep within the fragments, large intrusive bodies of tonalite, trondhjemite and granodiorite form interconnected networks, sometimes coalescing into composite batholith-sized masses. These intrusive complexes may cut older mafic and ultramafic rocks, engulfing blocks of greenstone sequences and older crust. At higher structural levels, remnants of volcanic and sedimentary cover sequences, including the greenstone belts derived from oceanic plateaus and island arcs, often occur as elongate belts or keel-like structures between more felsic domes. The contrast in mechanical strength between the relatively rigid felsic cores and the more ductile layered greenstones can lead to distinctive dome and basin patterns during deformation, with felsic rocks rising and greenstones wrapping around them. Even in the Archean, where subsequent tectonic events have overprinted many details, these patterns are recognizable in some well-preserved regions and provide clues about the assembly of early light crust. The chemical composition of tonalite, trondhjemite, granodiorite suites points to their derivation from basaltic sources under specific pressure and temperature conditions. High sodium content and particular trace element ratios indicate melting at depths where garnet is stable and plagioclase is absent or limited, consistent with lower crustal or upper mantle pressures. The presence of water in the source, inferred from mineral assemblages and geochemical signatures, is essential for lowering melting temperatures and enabling partial melts to form without complete breakdown of the source rock. These constraints imply that early continental fragments arise in zones where mafic crust is buried sufficiently deep and hydrated enough to undergo such melting conditions that can occur in thickened crust beneath arcs in underthrust or sagging plateaus and in regions of strong magmatic addition from below. Once formed felsic crust behaves differently under stress than mafic crust. Its lower density and different mineralogy influence how it responds to loading, heating and tectonic forces. Under compression, felsic bodies may fracture and form brittle fault networks near the surface, while deeper levels deform ductilely accommodating strain through crystal plasticity and flow. Their higher viscosity compared with surrounding mafic rocks can cause deformation to localize in adjacent weaker domains, focusing strain into greenstone belts and mafic layers. This contrast in rheology contributes to the segregation of felsic and mafic units into distinct structural positions within early crustal fragments. Over time, the accumulation of felsic material in certain regions leads to crust that is thicker and more buoyant than the global average. Such crust can resist subduction and recycling more effectively than thinner, denser oceanic lithosphere, increasing its likelihood of long-term survival in the geological record. Despite this relative stability, early continental fragments are not static. They interact with one another and with surrounding mafic terrains under the influence of Archean tectonic motions. Collisions between fragments can stack and thicken felsic crust, producing higher standing regions and more complex structural patterns. Lateral accretion of greenstone belts, volcanic arcs, and additional felsic intrusions along fragment margins increases their size and heterogeneity. Extension in some regions can thin the crust, create basins that trap sediments and promote new magmatic underplating and melting. In this way, early continental fragments grow, reshape, and sometimes break apart, yet they tend to remain preferential sites for the concentration of light crustal material. The exposure of felsic crust to surface processes has important consequences for the chemical evolution of the crust and ocean, even though the focus here remains on the physical development of the fragments. Felsic rocks weather differently than mafic rocks, producing abundant quartz and clay minerals and releasing different proportions of cations into solution. This affects the composition of sediments deposited in adjacent basins and the chemistry of rivers and coastal waters. Thick weathering profiles can develop on stable felsic surfaces, especially under warm, humid conditions, leading to intense leaching of mobile elements and the concentration of aluminum and iron-rich residuals. These weathered materials are then stripped away by erosion and redeposited as mature sediments such as quartz-rich sands and clay-rich mudstones in surrounding shallow seas. The presence of such sediments in Archean successions indicates that some felsic fragments remained exposed long enough to undergo substantial weathering and to supply distinctive sediment types to their margins. Thermal evolution within early continental fragments differs from that of surrounding mafic crust. Because felsic rocks have lower thermal conductivity and different heat production due to variations in radioactive element concentration, they can retain heat at depth and generate their own thermal regimes. Heat-producing elements such as potassium, thorium, and uranium tend to be more concentrated in felsic compositions. As a result, the interior of thick felsic crust may stay warmer for longer periods, influencing patterns of metamorphism and partial melting. In some cases, renewed melting within the felsic crust can produce more evolved magmas, including granites, with higher potassium content which intrude earlier, tonalite, trondhjemite, granodiorite complexes, and contribute to the compositional diversity of the fragments. This internal recycling of crustal material adds another layer of complexity to the structure of early continental blocks. The geometry of the contact between light felsic crust and underlying mantle is also important. Thick felsic fragments require compensating low-density roots or modifications in the underlying lithospheric mantle to maintain isostatic balance. In some regions, the mantle beneath early continental fragments may be cooled and chemically modified by prolonged melt extraction, producing depleted, mechanically strong lithospheric mantle sections. In others, the boundary between crust and mantle may be irregular, reflecting variable degrees of underplating and crustal thickening. Geophysical analogues from later times show that such variations can influence how crustal blocks respond to regional tectonic forces, guiding the localization of deformation and the propagation of faults. In the Archean, although direct geophysical data are absent, the preserved structural patterns and rock associations imply that similar variations in crust-mantle structure exist beneath early fragments. Together, these processes produce a surface environment in which patches of felsic crust stand higher than their surroundings and begin to function as the first continental fragments. They are characterized by thick accumulations of tonalite, trondhjemite, granodiorite intrusions, enveloped and flanked by deformed mafic and sedimentary sequences, and underlain by mantle that is starting to develop more stable, chemically distinct roots. The fragments vary in size and shape, and they are repeatedly modified by magmatism, deformation, and erosion, but they share the key property of being lighter and more buoyant than the predominantly mafic crust that covers most of the Archean Earth. Within this patchwork of high-standing felsic blocks and lower-lying greenstone and plateau terrains, the groundwork is laid for the assembly of more extensive, long-lived crustal regions that will occupy higher positions in the planet's outer shell and persist over very long geological timescales. As Archean felsic fragments thicken and accumulate more like crustal material, some evolve into more stable, long-lived regions that can be recognized as proto-cratons. A craton is a block of continental lithosphere that has cooled, thickened, and become mechanically strong enough to resist later deformation and recycling. In the Archean, this stabilization is a progressive process rather than a single event. It involves the assembly of multiple crustal terrains, the development of thick, buoyant crustal roots, and the cooling and chemical modification of the underlying lithospheric mantle. Together, these changes allow certain regions to stand higher and behave more rigidly than the surrounding more mobile parts of the lithosphere. Craton roots begin to form when early continental fragments and their attached greenstone belts are thickened by tectonic processes such as collision, lateral accretion, and magmatic underplating. As terrains assemble, lateral compression shortens the crust folding and faulting existing rocks and stacking them into thicker crustal sections. At the same time, continuous addition of magmatic material at depth, both from mantle-derived melts and from partial melting of the lower crust, contributes additional mass. This thickening increases pressure at the base of the crust, promoting metamorphic reactions that can transform basaltic lower crust into denser assemblages rich in garnet and other high-pressure minerals. In some settings, these dense lower crustal rocks may become gravitationally unstable and detach or sink deeper into the mantle. Their removal leaves behind a lighter, more silica-rich crustal column. Where this process is efficient, crustal sections with lower average density are produced, enhancing buoyancy and making them more likely to remain as high-standing, long-lived regions. Beneath these thickened crustal blocks, the mantle also evolves. Melt extraction during prolonged magmatism removes certain elements such as iron and calcium from the mantle, leaving a depleted, more magnesium-rich residue. This depleted mantle is less dense at a given temperature than fertile unmetasomatized mantle. As a result, when it cools, it can form a mechanically strong, buoyant lithospheric mantle root that supports the overlying crust. Over time, cooling and the addition of chemically distinct material, such as residues from melt extraction and possible small-scale underplating, produce a thick lithospheric keel that extends well below the crust mantle boundary. This keel is thermally and chemically distinct from the surrounding asthenospheric mantle and can reach depths of more than 100 kilometers in later cratons, though exact depths in Archean examples depend on the thermal state at the time. The combination of thick light crust above and depleted buoyant lithospheric mantle below yields a composite structure that is particularly resistant to later tectonic thinning and subduction. At the surface, regions evolving toward cratonic stability show patterns of rock assemblages and structures that reflect their assembly history. Large bodies of tonalite, trondhjemite, granodiorite form domes and batholiths that core these regions. Between and around them, greenstone belts occupy linear to arcuate zones that preserve sequences of volcanic and sedimentary rocks derived from earlier oceanic plateaus, island arcs, and shallow marine basins. These belts are often highly deformed with steeply dipping bedding, tight folds, and complex fault systems. The contrast in rheology between the stronger felsic plutons and the more ductile layered greenstones leads to structural patterns in which felsic domes rise relative to their surroundings, while greenstones are folded around them in synformal keels. This dome and keel geometry is a common feature in well-preserved Archean cratonic areas and indicates that vertical as well as horizontal motions play important roles in crustal reorganization during craton growth. Cratonic regions also show evidence for multiple episodes of magmatic addition and deformation. Early tonalite trondhjemite granodiorite suites can be intruded by later granites, with higher potassium content reflecting renewed melting of older crust and changing conditions of heat and water availability. Each magmatic pulse can be associated with local deformation metamorphism and the formation of new structures. Over time, this leads to a composite crustal block where rocks of different ages and origins are assembled into a coherent mechanically coupled unit. The internal architecture of such a block includes older cores that may approach stabilization surrounded and overprinted by younger additions that are still adjusting to the evolving stress and thermal fields. Despite this complexity, the overall effect is the gradual growth of areas where the crust is thick, felsic rich, and underlain by a depleted mantle root forming protocratons that will later host more extensive continental cover sequences. The thermal regime within emerging cratons differs from that in surrounding thinner lithosphere. Thick crust and mantle roots act as thermal blankets that slow the loss of heat from the interior. At the same time, the accumulation of heat-producing elements in felsic crust elevates radiogenic heating. Initially, this can maintain relatively high temperatures at mid-crustal levels, sustaining metamorphism and local partial melting. As time passes and the entire lithospheric column cools, geothermal gradients decrease, and the crust becomes more rigid and less susceptible to ductile flow. This transition from a warmer, softer state to a cooler, stronger one is a critical step in craton stabilization. Once the lithosphere has cooled sufficiently, large-scale deformation within these blocks becomes less likely, and subsequent tectonic activity tends to be partitioned along their margins or within weaker neighboring regions. Cooling also affects the style and extent of metamorphism. Early high-temperature, moderate to high-pressure metamorphism associated with crustal thickening and magmatic underplating gives way to lower temperature regimes, where only limited new metamorphic mineral growth occurs. In many cratonic areas, lower crustal rocks that once experienced high-pressure conditions remain as granulite facies, assemblages, while upper crustal rocks record greenschist to amphibolite facies, metamorphism. These metamorphic imprints, now exposed at the surface due to long-term erosion and uplift, provide evidence for the depth and intensity of processes that shape the craton roots. The transition to more rigid behavior is not instantaneous, but occurs over tens to hundreds of millions of years as heat diffuses away from the thickened lithosphere. During and after craton formation, the interplay between uplift and erosion begins to sculpt the surface. Thick, buoyant crust tends to rise isostatically as material is removed from the top. Erosion strips away high-standing areas, exposing deeper parts of the crust and transferring sediments to surrounding basins. Over long periods, this can remove large volumes of rock from cratonic interiors, smoothing relief and leaving broad low-relief surfaces that are characteristic of later stable cratonic landscapes. In the Archean, however, stabilization is still in progress, and cratonic regions may exhibit more varied topography, including belts of uplifted rocks and intervening basins that develop on and around the thickened crust. These basins can trap sediments derived from erosion of the craton and from neighboring active belts, building cover sequences that drape older basement. The composition of these sediments, often rich in quartz and stable heavy minerals, reflects the weathering of felsic and mixed source rocks. The boundaries between emerging cratons and surrounding mobile belts are zones of particular interest. Here, strong cratonic lithosphere abuts weaker, hotter lithosphere that is still undergoing active deformation, magmatism and recycling. Stress concentrates along these margins, and tectonic events such as subduction collision and strike-slip motion can reorganize crustal blocks and alter the shape of the craton edges. In some instances, new material is accreted to the craton margins in the form of volcanic arcs, sedimentary prisms, and additional felsic intrusions, widening the cratonic area over time. In other cases, parts of the craton edge may be thinned or modified by extension, and magmatic intrusion creating rift-like features that later evolve into new ocean basins or back arc regions. Through these processes, cratons do not remain entirely static. Rather, they act as long-lived cores around which younger tectonic activity is focused. The mechanical properties of cratonic roots are crucial for their persistence. The combination of chemical depletion, cooling, and thickness makes cratonic mantle roots strong and viscous compared with the underlying hotter asthenospheric mantle. This strength helps them resist deformation and detachment during convective flow. At the same time, their buoyancy makes them difficult to drag downward into the deeper mantle. These characteristics allow cratonic lithosphere to survive multiple cycles of tectonic reorganization in the surrounding regions without being fully reworked. Observations from later periods indicate that some cratonic roots retain signatures of very ancient depletion events, consistent with formation in the Archean, or even earlier. While direct sampling of Archean roots is limited, the preserved crustal rocks and mantle, derived xenoliths carried up by younger magmas, provide evidence that thick depleted roots are associated with ancient cratonic blocks. The stabilizing influence of craton roots extends upward into the crustal level, where their strength and buoyancy affect the stress field. Within cratonic interiors, the lack of strong lateral gradients and gravitational potential energy, compared with more strongly thickened or thinned regions, leads to reduced driving forces for internal deformation. In contrast, margins where thickness and density gradients are larger can experience higher differential stresses. As a result, tectonic strain during later events tends to localize along craton boundaries, leaving interiors relatively undeformed. This difference in behavior contributes to the preservation of Archean rock assemblies and structures within cratons, even when adjacent mobile belts record intense deformation and metamorphism. Over very long timescales, the combined processes of terrain assembly, crustal thickening, lower crustal modification, mantle depletion, and cooling transform some Archean regions from dynamic, strongly deforming systems into stable, strong lithospheric blocks. These blocks, recognized as cratons, form the kernels of larger continental masses that will later amalgamate. In the Archean context, they coexist with extensive areas of more mobile mafic-dominated lithosphere, creating a planet where rigid, buoyant continental cores are interspersed with belts of active volcanism, sedimentation, and deformation. The emergence of craton roots and growing land masses thus marks a stage at which parts of the Earth's outer shell begin to exhibit long-term stability, even while neighbouring domains continue to evolve rapidly. In this patchwork lithosphere, the next step inward concerns the overall style of tectonic deformation that operates on hotter Earth, and how it redistributes and reshapes both the stable cratons and the more mobile terrains around them. On a hotter Archean Earth, the style of tectonic deformation that shapes the lithosphere reflects high internal heat flow, thin and thermally soft lithospheric plates, and strong contrast between buoyant felsic fragments and denser mafic domains. The outer shell does not behave as a single rigid plate mosaic, identical to that of later times, yet it does not remain a simple, undifferentiated skin either. Instead, the observable rock record suggests a combination of vertical and horizontal motions with dense volcanic and sedimentary piles sinking relative to lighter felsic cores, crust thickening and thinning under changing stress fields, and large-scale shear zones transporting blocks laterally. The exact balance of these processes is still uncertain, but several broad features can be outlined from preserved structures in Archean cratons and greenstone belts. One important aspect is the tendency for dense supracrustal rocks, mainly mafic volcanic and associated sediments, to occupy keel-like positions flanking or underlying felsic domes. In many Archean terrains, greenstone belts form steeply dipping folded packages that wrap around or lie between more massive tonalite trondhjemite granodiorite bodies. This architecture suggests that denser layered volcanic and sedimentary sequences have moved downward relative to lighter, intrusive complexes. Such vertical motions can occur when the lower parts of thick supracrustal piles become gravitationally unstable and sink into a warmer, weaker lower crust or upper mantle, a process sometimes described as subduction. As these greenstone successions descend, more buoyant felsic material can rise between and above them, producing dome structures. In this way, vertical mass redistribution contributes significantly to crustal reorganization in a hot lithosphere where viscosity contrasts between units are large and strength is reduced at depth. Horizontal deformation also plays a clear role in the Archean. Many greenstone belts display evidence for substantial lateral shortening, including tight folds, thrust faults, and imbricate stacking of volcanic and sedimentary slices. These structures indicate convergence between crustal segments, with material being pushed together, stacked and thickened. In some areas, distinct volcanic and sedimentary terrains, with different histories and compositions, are juxtaposed along major fault zones, implying lateral transport and accretion of crustal blocks. Such patterns are consistent with some form of horizontal tectonic motion, in which parts of the lithosphere move relative to one another and interact along zones of compression and shearing. The scale and continuity of these motions may differ from modern plate tectonics, but the basic mechanical principle of lateral convergence and terrain assembly is present. High heat flow and thin lithosphere modify how these vertical and horizontal processes operate. In a hotter planet, the lithosphere is generally weaker, especially in its lower parts, and the transition to ductile behavior occurs at shallower depths than in cooler later eons. This promotes distributed deformation over broader regions rather than strongly localized strain along a few narrow plate boundaries. Thick volcanic plateaus and arcs may deform internally through folding boudinage and lower crustal flow, while lighter felsic fragments respond differently, focusing strain into surrounding mafic belts and shear zones. The lower crust, warmed by magmatic underplating and radioactive heat production, can act as a low-strength channel that allows lateral flow of material away from zones of thickening, smoothing out topographic and gravitational contrasts over geological timescales. In some settings, evidence suggests that dense lower crustal sections have detached and sunk into the mantle as drips. Where this occurs, downward flow of dense material and compensating upward flow of hotter, lighter mantle create complex patterns of vertical motion. Surface expressions can include localized subsidence and uplift changes in the distribution of metamorphic grades and variations in magmatic output. The removal of dense lower crust reduces the average density of the remaining crustal column, aiding the stabilization of light felsic regions. These drip and foundering processes fit naturally into a hotter Earth, where density contrasts between a clogitized lower crust and surrounding mantle are large, and where viscosity is low enough to permit such motions on reasonable timescales. Shear zones are another key feature of Archean tectonic style. Large through-going zones of intense deformation, often kilometers wide, cut across greenstone belts and felsic plutons. Within these zones, rocks are strongly foliated, lineated and recrystallized, indicating significant ductile and brittle strain at different levels. Some shear zones accommodate lateral strike-slip motion between crustal blocks, while others combine strike-slip and dip-slip components, enabling oblique convergence or extension. The presence of such zones shows that part of the strain imposed by regional stress fields localizes along preferred structural pathways even in a generally warm and weak lithosphere. These shear zones guide the relative movement of terrains, influence the ascent of magmas, and later control patterns of uplift and erosion. Metamorphic patterns in Archean terrains provide additional constraints on deformation regimes. Many greenstone belts preserve gradients in metamorphic grade that correspond to depth variations produced by burial and exhumation. In some cases, belts exhibit relatively low temperature, low pressure metamorphism, consistent with shallow burial, while adjacent deeper crustal levels show high temperature, moderate pressure assemblages. The arrangement of these metamorphic domains suggests that crustal thickening burial and later exhumation have occurred in response to both vertical subduction and horizontal convergence. In some regions, paired or contrasting metamorphic belts are observed, with one belt recording higher pressure conditions and another lower pressure conditions for similar ages. These patterns may hint at early forms of subduction or underthrusting, where one crustal slice is forced beneath another, but the limited and overprinted nature of the record makes firm interpretation difficult. Basin formation and destruction under Archean tectonic regimes also reflect the interplay of vertical and horizontal motions. Depressions form where crust is thinned by extension, where flexural loading occurs adjacent to thickened crustal blocks or volcanic piles, and where dense lower crust founders. These basins act as sites for sediment accumulation, recording the erosion of uplifted areas and the ongoing volcanic and chemical fluxes of the surface environment. As tectonic conditions change, some basins are inverted during compression, with former deeper centers becoming uplifted and folded, while others are preserved and incorporated into thicker crustal sections. The resulting stratigraphic package is now deformed and metamorphosed archive sequences of subsidence filling and uplift, tied to the changing stress regime in a hot evolving lithosphere. The variability of Archean tectonic style across different regions is significant. Some cratonic areas show evidence for strong vertical movements and dome-kill structures dominating crustal architecture, suggesting that subduction and vertical density-driven flow are particularly important there. Other areas display clearer signatures of lateral accretion, large-scale thrusting and possible early subduction, like behavior where ophiolitic fragments or high-pressure rocks appear to record burial to significant depths and return. It is possible that multiple tectonic modes operate at the same time or in succession, with regions of more modern-style plate interaction coexisting with domains dominated by vertical tectonics and lower crustal flow. The controlling factors likely include local heat flow, lithospheric thickness, presence or absence of buoyant felsic crust, and distribution of plate boundary forces. Over time, as mantle temperatures slowly decrease, the balance among these modes shifts. Early in the Archean, high temperatures favour distributed vertical and drip-like processes, while later in the Eon cooler conditions and thicker lithosphere may permit more sustained organised plate interactions and longer-lived subduction zones. The rock record captures only fragments of this evolution, filtered through later deformation and metamorphism, so reconstructions must rely on incomplete evidence and on physical models consistent with observed structures and compositions. Even with these uncertainties, the key outcome is clear. By the end of the Archean, the planet's outer shell operates as a mosaic of mechanically distinct blocks, some thickened and stabilized as cratons with strong roots, others thinner and more mobile, and all influenced by the high internal heat that drives vigorous deformation. Within this mosaic, tectonic styles on a hotter Earth control which regions rise, which sink, and how crustal material is redistributed between felsic continental fragments, mafic greenstone belts, and underlying mantle. These motions in turn regulate the spatial pattern of volcanic activity, the locations of basins and uplifts, and the pathways along which heat and material move between deep interior and surface, setting the stage for the more detailed roles of mantle convection and heat transport that operate further inward in the system. Beneath the Archean crust, the mantle convects as a slowly deforming solid that transports heat from the deep interior toward the surface. Convection in this context means that hotter, slightly less dense mantle material rises, while cooler, slightly denser material sinks, setting up large-scale circulation patterns. Because the Archean Earth retains more internal heat from accretion, core formation, and radioactive decay than in later eons, the temperature contrast driving this motion is greater, and the viscosity of mantle rocks is lower. These conditions favour vigorous convection, with stronger upwellings and downwellings, and shorter timescales for material exchange between deep and shallow levels. The lithosphere, which includes the crust and the uppermost rigid mantle, forms the upper thermal boundary layer of this convecting system. Heat escapes from the mantle through this layer by conduction and by advection, where magmas ascend and erupt. The thickness and strength of the lithosphere vary from place to place depending on age composition and thermal state. Young lithosphere over upwelling mantle is thin and hot. Older lithosphere away from active magmatic centres is thicker and cooler. In the Archean, overall lithospheric thickness tends to be smaller than in later times, because high heat flow limits the depth to which rocks can remain cold and rigid. This thin, warm lid allows stresses from mantle convection to couple more effectively to the surface, contributing to the pronounced deformation and magmatism observed in Archean terrains. Upwelling regions in the mantle correspond to zones where hotter material rises toward the base of the lithosphere. These upwellings can take the form of broad diffuse regions or more focused plume-like structures. As mantle material ascends, it experiences lower pressure, which reduces its melting temperature relative to the ambient temperature. When the actual temperature exceeds the solidus at a given depth, partial melting begins. The melt being less dense than the solid residue separates and migrates upward, feeding volcanic systems that build oceanic ridges, plateaus and arcs at the surface. In the Archean higher mantle, temperatures mean that melting can occur over thicker vertical intervals and at greater degrees of partial melting than in later eons, producing abundant basaltic and komatiitic magmas. The extraction of melt leaves behind a residuum that is depleted in fusible components and has a different mineralogy and density than the original mantle. Over time, repeated melting and melt extraction in upwelling regions create chemically distinct domains within the mantle, including buoyant depleted mantle that can become part of lithospheric roots beneath stable crustal blocks. Downwelling regions correspond to places where cooler, denser material sinks from the base of the lithosphere into the deeper mantle. In later plate tectonic regimes, such downwellings are associated largely with subduction of cold oceanic lithosphere. In the Archean, with thinner lithosphere and different tectonic styles, downwelling may involve a combination of foundering of dense lower crust sinking of thickened mafic lithosphere and localized subduction-like behavior where cold slabs descend. Gravity acts on regions where density is increased by cooling compositional changes or phase transitions pulling them downward. As material sinks, it carries surface-derived components such as hydrated minerals and previously depleted mantle deeper into the convecting system. This process helps recycle heat-producing elements and volatile bearing phases into the interior, influencing long-term thermal and chemical evolution. The pattern of mantle convection is three-dimensional and time-dependent. Large-scale cells may span thousands of kilometers, with broad upwellings beneath regions of extended or thinned lithosphere, and downwellings beneath zones of crustal thickening and cooling. Superimposed on these are smaller scale features such as plumes and drips. Plumes arise where instabilities in the thermal boundary layer at the core mantle boundary or within the lower mantle produce rising columns of hotter material. Drips form where dense lower lithosphere or lower crust detaches and sinks. In the Archean higher Rayleigh numbers, which express the sensitivity of convection to temperature contrast, layer thickness, viscosity and thermal expansivity, favour more vigorous and possibly more chaotic convection patterns than in cooler times. However, even in this vigorous state, the motion remains slow on human timescales, with velocities measured in centimetres or a few tens of centimetres per year. Heat leaves the Archean mantle through three main pathways: conduction through the lithosphere advection, by rising magmas, and advection by solid-state flow within the convecting mantle. Conduction dominates across the cold, uppermost thermal boundary layer where temperature gradients are steep. The heat flux conducted through this layer is higher in the Archean because interior temperatures are elevated and boundary layers are thinner. Magmatic advection occurs when melts generated in the mantle ascend and cool in the crust or erupt at the surface. The crystallization of these melts releases latent heat and transfers thermal energy from depth toward the upper crust and hydrosphere. Solid-state advection operates as convecting mantle moves hot material upward and cooler material downward. The relative importance of these pathways changes as the Earth cools, but in the Archean magmatism plays a particularly prominent role because high mantle temperatures produce large volumes of melt. Evidence for vigorous Archean mantle convection and high heat flow comes from several geological observations. The presence of komatiites, which require very high eruption temperatures and high degrees of melting points to a hotter mantle. The widespread occurrence of thick oceanic plateaus and large igneous provinces indicates substantial melt generation over broad areas. High geothermal gradients inferred from metamorphic assemblages in some Archean terrains suggest that heat flow through the crust was elevated. At the same time, the preservation of early cratonic roots implies that some regions cooled and strengthened sufficiently to resist later reworking, meaning that mantle convection must accommodate both strong stable blocks and weaker, more deformable domains. The interaction between convecting mantle and overlying lithosphere influences where these differences arise. Where ascending mantle flows beneath thin lithosphere enhance melting, and magmatism thin the lid further and keep it hot and weak, maintaining a mobile, deformable region. Where thickened crust and depleted mantle roots develop heat flow, decreases locally, the lithosphere cools and thickens, and the strong cratonic keels alter flow patterns in the underlying mantle, deflecting upwellings and guiding downwelling currents around or along their edges. In this way, mantle convection and lithospheric structure co-evolve, each shaping the other over hundreds of millions of years. As the Archean progresses, secular cooling gradually reduces mean mantle temperatures. This cooling arises because heat loss through the surface exceeds internal heat production and residual primordial heat. With time, lower mantle temperatures decrease the degree of partial melting for a given pressure, reduce the frequency and intensity of komatitic magmatism, and allow lithospheric plates or blocks to thicken and strengthen. The vigour of convection decreases as viscosity increases, and the scale and style of convective cells evolve. These long-term trends are not necessarily smooth. Episodes of enhanced magmatism and crustal growth can still occur where localized upwellings or mantle instabilities concentrate heat and melt generation. Yet the overall direction is toward a mantle that supports thicker, more rigid lithosphere, favouring a transition toward more modern style plate interactions in younger eons. The convecting mantle also redistributes chemical heterogeneities generated by partial melting and melt extraction. Depleted mantle domains enrich domains where melts have pooled and crystallized, and regions that have incorporated subducted or foundered material are stretched, folded, and transported by convective flow. Some domains become part of the deep mantle, possibly residing near major internal boundaries for long periods, while others are returned toward the surface in later upwellings. In the Archean, when convection is vigorous, this internal mixing is efficient on large scales, but strong, buoyant lithospheric roots beneath cratons can isolate parts of the upper mantle from direct participation in deeper circulation, preserving ancient depletion signatures. This interplay between convection and chemical differentiation means that by the end of the Archean, the mantle is no longer chemically uniform. It contains inherited structures that influence how and where melts will form in subsequent geological periods. From the perspective of the surface mantle, convection manifests as patterns of volcanism, uplift subsidence and heat flow that change over time. Regions above upwellings tend to experience higher heat flow, more frequent magmatic events, and elevated topography due to thermal buoyancy. Regions above downwellings tend to cool and subside, forming basins and zones of thickened lithosphere. The Archean distribution of greenstone belts, cratonic blocks, and major igneous provinces can be viewed as the surface expression of these deep convective processes operating under conditions of high internal heat. Within this framework, the generation of magmas and their role in crustal differentiation represent the next step inward, as partial melting in specific mantle and lower crustal settings converts convective heat transport into the construction and modification of the solid outer shell. Magma generation in the Archean Earth links the deep convecting mantle to the evolving crust, converting thermal and chemical gradients into new rock that reshapes the outer shell. Partial melting occurs whenever mantle or lower crustal material crosses conditions where the temperature is high enough relative to pressure and water content to begin producing liquid from solid assemblages. Because rocks are mixtures of minerals with different melting points, melting begins over a range of temperatures, and only part of a rock need melt to generate magma. The resulting melts are generally less dense and more mobile than their solid source, so they tend to migrate upward, pooling, stalling, or erupting depending on local structures and density contrasts. In the Archean higher mantle, temperatures and abundant water in some source regions allow partial melting to occur more frequently and over larger volumes, generating substantial quantities of magma that build new crust and modify older crustal sections. In the upper mantle beneath young, thin lithosphere, decompression melting is a primary mechanism for generating mafic magmas. As hot mantle rises in upwelling regions such as beneath spreading centres, oceanic plateaus and plume heads, the pressure decreases faster than the temperature moving the material into the melting field. At a given depth, the degree of partial melting depends on the starting temperature composition and water content. In the hotter Archean, mantle degrees of melting can be high-producing ultramafic komatitic melts, in addition to more common basaltic magmas. Komatitic melts, with their high magnesium and low viscosity, originate at greater depths and higher temperatures than most basalts, and can ascend rapidly, sometimes with limited interaction with the overlying lithosphere. Basaltic melts generated over a broader range of conditions may pond at the base of the crust, or within it, crystallizing slowly as intrusive bodies or ascending further to erupt on the surface. Together, these magmas construct thick volcanic sequences and intrusive complexes that make up a large portion of Archean oceanic and plateau crust. In addition to decompression melting, flux melting and internal heating in the lower crust contribute to magma generation. Where hydrated oceanic crust is buried or underthrust into hotter regions, water released from breakdown of hydrous minerals lowers the solidus of surrounding rocks, allowing melting at lower temperatures than would otherwise be required. This process can occur in thickened mafic crust under arcs in lower crustal roots, beneath plateaus, and beneath early continental fragments that have accumulated substantial mafic material at depth. Heat input from underplating mafic magmas further raises temperatures in these zones. As a result, parts of the lower crust begin to melt, producing felsic magmas that are richer in silica and alkalis than their mafic sources. These melts can segregate from their residues and move upward, forming tonalite trondhjemite granodiorite plutons that contribute to the growth of light continental crust. Residual rocks left behind are denser and more mafic, sometimes evolving toward garnet-rich assemblages that may subsequently sink if they become gravitationally unstable. The pathways that magmas follow from their source to their final emplacement sites influence how they evolve. As melts rise through the mantle and crust, they may stall where their density approaches that of the surrounding rocks, or where structural barriers such as changes in rheology or pre-existing intrusions impede further ascent. In these temporary reservoirs, magmas cool and begin to crystallize minerals. Early formed crystals can settle or be left behind as residual solids if more melt, escapes changing the composition of the remaining liquid. This process of fractional crystallization allows a single primary melt to produce a spectrum of derivative magmas with different compositions. In mafic magmatic systems, early crystals often include olivine pyroxene and calcium-rich plagioclase, which remove magnesium, iron, and calcium from the liquid, driving the residual melt toward higher silica and alkali contents. Over time, repeated cycles of melt injection, crystallization, and extraction in crustal magma chambers produce differentiated intrusive bodies and volcanic suites, whose compositions record these internal processes. Interaction between ascending magmas and surrounding rocks, or assimilation, is another mechanism of crustal modification. When hot magmas intrude into cooler crust, they can partially melt, or react with the wall rocks. If the resulting melts or dissolved components mix into the magma, they alter its composition. In the Archean, where early felsic crust and thick mafic crust both exist, mafic magmas rising through felsic regions may become more evolved by assimilating silica-rich material, while felsic melts traversing mafic sections may incorporate mafic components. The extent of assimilation depends on temperature contrasts, the availability of wall rock that can melt, and the time magmas spend in contact with their surroundings. Combined with fractional crystallization, assimilation contributes to the compositional diversity of Archean igneous suites, and helps link magma generation to the broader process of crustal differentiation. As magmas solidify, they do so in various structural settings. Some crystallize at depth as large plutons and batholiths that build the cores of continental fragments. Others form sheet-like sills and dikes that cut across existing structures, recording the directions of stress and providing pathways for heat and mass transfer. Still others reach the surface and erupt as lava flows, pyroclastic deposits, and volcanic lastics, adding material to the upper crust and seafloor. The balance between intrusive and extrusive emplacement affects how much heat is retained in the crust and how quickly magmatic systems cool. Intrusive bodies cool slowly, providing long-lasting heat sources that drive metamorphism and further melting in their surroundings. Extrusive products cool quickly at the surface or seafloor, transferring heat efficiently to the hydrosphere and atmosphere. In the Archean, with high magma production rates, both intrusive and extrusive components are abundant, but the thick intrusive complexes associated with tonalite trondhjemite granodiorite crust play a particularly significant role in building stable, buoyant crustal blocks. Crustal differentiation through these magmatic processes gradually changes the average composition and structure of the lithosphere. Initially, much of the crust is mafic, formed directly from mantle, derived basalts and komatiites. With time, partial melting of this mafic crust, fractional crystallization and assimilation produce increasing volumes of intermediate and felsic rocks. These rocks, being less dense, tend to concentrate in higher structural positions and in regions where crust has been thickened and heated sufficiently to allow extensive melting. The resulting crust becomes stratified with more mafic compositions tending to occupy lower levels and felsic compositions dominating upper and central parts of thickened blocks. This vertical compositional layering influences how the crust responds to later tectonic stresses and thermal changes, because rocks with different mineralogical compositions have different strengths, melting points and densities. The chemical evolution of the crust is reflected not only in bulk compositions but also in trace element and isotopic signatures. During partial melting, some elements preferentially enter the melt while others remain in the solid residue. Repeated cycles of melting and melt extraction therefore concentrate certain incompatible elements in the crust relative to the mantle. Isotopic systems, such as those involving strontium, neodymium and hafnium, record the timing and extent of crustal extraction and recycling. In the Archean, these systems show that significant volumes of continental crust are generated early, and that some crustal blocks experience multiple episodes of magmatic addition and reworking. Although the detailed interpretations of these signatures require careful analysis, the broad implication is that magma generation and differentiation contribute steadily to the long-term separation of crust and mantle compositions, establishing chemical distinctions that persist into later eons. Thermal feedbacks link magma generation to the mechanical state of the crust. Magmatic additions bring heat into the lower and middle crust, weakening rocks and making them more susceptible to ductile deformation and flow. This can promote further crustal thickening, where convergence is active as softened lower crustal layers spread laterally or flow toward regions of lower pressure. In areas of extension, heated crust may thin more readily forming basins that trap sediments and new volcanic sequences. Overlying intrusive bodies can act as rigid caps, while their hotter, weaker roots deform beneath them. As magmatic activity wanes and the crust cools, it strengthens, reducing the rate of deformation and allowing structures formed during active magmatism to freeze in place. In this way, phases of intense magma generation correspond to periods of active crustal reorganization, while quieter magmatic intervals allow partial stabilization and preservation of the resulting crustal architecture. The density structure produced by magmatic differentiation also influences the fate of different crustal levels. Dense residues of partial melting in the lower crust and upper mantle, including rocks rich in garnet and iron, increase the likelihood of gravitational instability. If such layers become thick enough, they may begin to sink into the underlying mantle, a process that removes dense material from the base of the crust and allows lighter, more felsic rocks above to rise isostatically. This foundering helps maintain the low average density of emerging continental crust and prevents indefinite accumulation of dense lower crustal material. At the same time, the sinking residues carry heat-producing elements and other components back into the mantle, where they may participate in later melting events. Thus, magma generation and crustal differentiation operate within a cycle that both builds and prunes the crust, regulating its thickness composition and buoyancy over Archean time. Viewed at the scale of whole crustal blocks, Archean magma generation and differentiation produce a patchwork of domains with different compositions, ages, and thermal histories. Some regions are dominated by thick mafic sequences with limited felsic intrusion, others by large tonalite trondhjemite granodiorite complexes surrounded by deformed greenstone belts, and still others by mixed assemblages reflecting multiple overprinting events. Each magmatic episode leaves behind solidified bodies that become part of the structural framework for later deformation and magmatism. The arrangement of Pluton's volcanic successions and metamorphic units records successive stages of crustal growth and modification, while later tectonic processes will continue to reshape these domains. The fundamental patterns of Archean crustal differentiation arise from the ways in which partial melting, melt migration, and solidification redistribute material and heat between mantle, lower crust, and upper crust. Against this background of large-scale magma generation and crustal change, smaller-scale interactions between hot rock circulating fluids and existing minerals operate throughout the Archean lithosphere. Wherever magmas intrude, cool, and crystallize, they release heat and drive movement of fluids through surrounding rocks. These fluids derive from magmas themselves and from pore waters, and metamorphic reactions in the host rocks react with minerals and modify their compositions and textures. The results include zones of altered rock around intrusions, networks of veins, and subtle chemical gradients that together record the pathways of fluid flow and the conditions of water-rock interaction within the Archean crust. Within the Archean crust, hydrothermal circulation moves water through hot rock, linking surface reservoirs to deeper levels and creating zones where fluid and mineral continuously react. Seawater enters the crust through fractures, faults, and porous layers in oceanic plateaus, volcanic islands, and newly formed seafloor. Meteoric water derived from rainfall and surface runoff on emergent land can penetrate felsic fragments and their margins. In both cases, gravity and pressure gradients drive fluids downward along permeable pathways, while heat from underlying magmas cooling intrusions and elevated geothermal gradients warms the water as it descends. As fluids gain heat and dissolve components from the surrounding rocks, their density and composition change. Buoyancy forces then guide them back upward along focus channels or diffuse zones, closing convection loops that can persist as long as sufficient permeability and heat are available. Near mid-ocean ridges and thick Archean plateaus, high-temperature hydrothermal systems develop where seawater circulates through permeable basalt komatiite and associated volcanic rocks. Fluids can reach temperatures of several hundreds of degrees Celsius at depths of a few kilometers, depending on local pressure and the position of heat sources. At these temperatures, water acts as a powerful solvent, especially when mixed with magmatic gases such as carbon dioxide and sulfur species. It leaches alkali and alkaline earth elements, silica metals and volatiles from primary minerals. As heated fluids rise toward cooler levels, their ability to hold these dissolved components decreases, and reactions occur that precipitate new minerals and alter existing ones. Wider regions of lower temperature circulation where fluids remain below roughly 100 degrees Celsius also occur in the upper crust and along the flanks of hotter systems. In these zones, reaction rates are slower, but long residence times allow progressive alteration of rock and gradual exchange of elements between fluid and solid. The pathways that hydrothermal fluids follow are controlled by the evolving structure of the crust. Fractures generated by tectonic stresses, cooling contraction, and intrusive emplacement form the major conduits. Vesicular zones in lava flows, breccias filled with open spaces and porous sediment layers provide additional routes. As fluids move through these pathways, mineral precipitation can both enhance and reduce permeability. For example, dissolution of feldspar and mafic minerals can enlarge pore spaces and fractures, while growth of quartz carbonates and sulfides can clog them. This feedback means that hydrothermal circulation is spatially and temporally variable, with channels opening and closing as alteration progresses. In Archean terrains, later deformation and metamorphism may reorient or overprint these pathways, but the mineral assemblages and textures preserved in veins, alteration halos and replaced rock volumes still retain information about the former flow network. Basaltic and ultramafic rocks are particularly susceptible to hydrothermal alteration. When seawater or mixed fluids penetrate these rocks, They react with olivine pyroxene and plagioclase to form secondary minerals such as chlorite, actinolite, epidote, albite, and various clay minerals. Iron may partition into oxides or sulfides depending on redox conditions. Magnesium and calcium can be removed from the fluid or the rock, depending on the direction of reaction. In ultramafic rocks, hydration can produce serpentine and related minerals in a process commonly termed serpentinization. This reaction not only changes mineralogy, but also releases heat and hydrogen, altering both thermal and redox conditions locally. The altered rocks show characteristic greenish colours, fine-grained textures, and specific mineral assemblages that distinguish them from their unaltered counterparts, even after later metamorphism has modified them further. Felsic rocks within early continental fragments also undergo hydrothermal alteration, though the details differ because their primary minerals include quartz, feldspars, and micas. Fluids moving through tonalite, tronjamite, granodiorite and related rocks can cause potassium or sodium enrichment or depletion silica addition, or removal and growth of new micas, epidote and amphiboles. In many Archean complexes, zones of potassic sodic or calcic alteration surround intrusive bodies or occur along shear zones, recording prolonged fluid-rock interaction as magmatic heat drives convective circulation. These alteration patterns sometimes focus along faults and fracture networks that later become important structural features. The distribution of altered zones thus reflects both the geometry of fluid flow and the stress field that produced and maintained the pathways. Hydrothermal systems are responsible for concentrating various metals into mineral deposits. As fluids leach copper, zinc, lead, iron, and other metals from large rock volumes, they transport them in solution, as chloride, sulfide, or other complexes. When these fluids encounter changes in temperature, pressure, pH, or redox state, their capacity to carry metals drops and ore minerals precipitate. Along seafloor vent sites, high-temperature fluids mix with cold seawater, causing rapid precipitation of sulfide minerals such as pyrite, chalcopyrite, sphalerite, and galena. These precipitates build up chimneys and mounds on the ocean floor, and create stockwork networks in the underlying rocks. Over time, burial and tectonic deformation can convert these systems into massive sulfide deposits preserved within greenstone belts. In the deeper crust and along shear zones, lower temperature hydrothermal fluids can form quartz veins, containing sulfides, native gold, and other mineral assemblages. Although details of specific deposits vary from place to place, the common underlying process is repeated dissolution of metals in one part of the flow system, and their precipitation elsewhere, guided by fluid pathways and local chemical conditions. As attention moves inward to smaller scales, the interface between hydrothermal fluids and minerals becomes the central focus. At grain boundaries, crystal defects and microfractures, fluid molecules and dissolved ions meet solid phase surfaces. Here, dissolution and precipitation proceed through a series of elementary reactions. At favourable sites such as high-energy edges and corners of crystals, atoms detach from the solid and enter solution, while in supersaturated conditions, new crystals nucleate and grow. Replacement reactions occur when one mineral dissolves while another precipitates in its place, often preserving the overall shape of the original grain or rock fabric while changing its composition. Over time, these microscale processes transform the mineralogy and texture of the rock, producing features such as pseudomorphs, zoning in individual crystals, and finely intergrown mineral assemblages. Even when later metamorphism modifies the larger scale appearance of rocks, these replacement and growth patterns can survive in protected domains. Fluids carry isotopes of key elements, and fractionation of these isotopes during water-rock interaction leaves subtle but measurable signals in minerals and fluid inclusions. Oxygen isotopes in silicate and carbonate minerals record the temperature and composition of the fluids with which they are equilibrated. At higher temperatures, isotopic fractionation between mineral and fluid is smaller. At lower temperatures, it is larger. Hydrogen isotopes in hydrous minerals and fluid inclusions reflect the sources and evolution of water, including contributions from seawater, meteoric water, and magmatic fluids. Carbon isotopes in carbonate minerals and in carbon-bearing phases influenced by inorganic processes indicate the balance between dissolved carbon species and the conditions under which they precipitate. Sulfur isotopes in sulfides and sulfates capture information about redox state and sulfur sources including volcanic gases, seawater-derived sulfate and reduced sulfur species produced by various chemical reactions. Silicon isotopes in cherts and silica-rich alteration products can provide clues about the temperatures and processes of silica mobilization and deposition. In Archean rocks, these isotopic systems are often overprinted by later events, but careful analysis of specific mineral domains that remained closed to diffusion can still reveal the conditions of Archean hydrothermal activity. Fluid inclusions are another key microscale record. As minerals grow from hydrothermal fluids, they can trap tiny pockets of the fluid within them. These inclusions, often only micrometers across, are sealed off from the external environment as crystals continue to grow. The composition density and phase behavior of the trapped fluid reflect the conditions at the time of entrapment. By heating and cooling these inclusions in laboratory experiments and observing phase changes, it is possible to infer temperatures and pressures of formation, as well as salinity and volatile content. In Archean quartz, veins, cherts, and other minerals, inclusions preserve snapshots of ancient fluids, including brines related to seawater modified by water-rock interaction, and fluids with strong magmatic or metamorphic components. Together with isotopic data and mineral assemblages, they provide a detailed view of the physical and chemical environment of Archean hydrothermal systems on scales far smaller than can be seen in the field. Microstructures in minerals such as zoning patterns, exsolution, lamellae, and deformation features also encode information about thermal and chemical histories. Zoning in plagioclase amphiboles and other minerals can reflect changes in fluid composition, temperature, or pressure during growth. Exsolution textures in pyroxenes and feldspars can record cooling rates and later re-equilibration. Deformation twins, subgrain boundaries, and recovered dislocation structures can indicate episodes of stress and annealing linked to tectonic events and metamorphic overprints. Although these features are not exclusive to hydrothermal environments, many develop in response to conditions created or modified by fluid flow and heat transfer. In Archean terranes, they contribute to reconstructing the sequence of heating, cooling, deformation, and fluid movement that occurs during and after hydrothermal activity. The cumulative effect of hydrothermal circulation and microscale water rock reactions in the Archean is a crust that is extensively altered, chemically zoned, and enriched in secondary minerals and isotopic signatures. Large volumes of basalt and ultramafic rock transform into greenstone assemblages through hydration and metamorphism, while felsic plutons acquire alteration halos and vein systems. Metals become concentrated into ore deposits that sit within or adjacent to these altered zones. Seawater compositions evolve as elements are transferred into and out of the ocean through these same processes, and the isotopic compositions of major elements in seawater shift accordingly. The small-scale records preserved in minerals and fluid inclusions thus integrate signals from broad-scale circulation systems that move heat and material between mantle crust and hydrosphere. In studying these Archean rocks, it is possible to trace connections from planetary-scale convection through crustal magmatism and tectonics down to the level of individual mineral grains and tiny pockets of trapped fluid. Each level of this system reflects interactions among water rock heat and chemical species. By the close of the Archean, the first stable oceans rising continental fragments and evolving crustal roots are all intertwined with a network of hydrothermal pathways and microscopic records that quietly store information about the physical and chemical state of the early Earth.